Okay, so maybe I say just a few words before we start. It's a pleasure to welcome you all here. I guess it's one of the first hybrid conferences. So there are 6 of us here in the room, and everyone else is online. And we're very grateful to the University of Chicago Center for hosting our conference. And we're looking forward to 3 exciting days of metric geometry. So I now bring the camera. So maybe you can see. So yeah, Bernard.
Okay, thank you, Tony. Yes, we are grateful to the University of Chicago, and I'm happy to introduce Lorenzo Fantini, who is our first speaker this morning, and who will talk, as you see on your screen, about metric geometry of complex surfaces, Lipschitz Normal Embeddings, and polar exploration. So Lorenzo. We'd like to hear from you.
Thanks a lot. Thank you all. It's my pleasure to open this conference. Thanks so much for the invitation. Sadly, I could not be there in person this morning, but I'm with you in spirit and I'll give you this talk remotely. And as you see here, so I think you can see when I do this, right? This talk is going to be the first part of a 3-part mini course that I'm going to give with Andrea Bellotto da Silva and Dan Pichon. I'll say a little bit more about the contents of the mini course in a moment. Let me just say first that if you have any questions, you can feel free to interrupt me. You can just unmute yourself and ask me the question, or drop it in chat. I will try to keep an eye on the chat. If I fail to, please, someone there can interrupt me and tell me. So before the context, let me just say a few words about the underlying math as a very simple introduction. So this is all very classic. I'm interested in the local structure of a singularity. So my starting datum consists of a complex variety, either algebraic or analytic, with an isolated singularity, which is traditionally called 0. And I studied this by embedding it inside a smooth space, like this. This is my germ X. Here I have the singularity, and I consider the intersection of this variety with a small ball, because this is everything I need to know topologically. Precisely, there is a very well-known result that tells me that topologically, this germ is nothing else than the cone over the intersection with this sphere. Okay, so the intersection here, which I've drawn in blue, is the intersection of my singular germ with the border of the boundary of the ball, and what's usually called the topological link of the singular germ. And then the theorem tells me that this intersection does not depend on the choice neither of an embedding nor of a very small radius for this sphere. So it's a well-defined real manifold. So topologically, in a way, there's not much more than the link. If I understand the link, I understand everything. But I can try to make the problem a bit more interesting by adding further structure to the situation. And I do this by considering 2 different metrics on the singular germ. The simplest one is the so-called outer metric, which is given by simply measuring the distance. Maybe I'll just throw it here. I have 2 points on my germ, and I measure their distance in Cn. This is the outer metric. And the inner metric is given by measuring the length of paths connecting the 2 points and living inside the singular germ, though the term inner. And these metrics have been studied extensively by a branch of singularity theory, which is called the Lipschitz geometry, which has been extensively studied, especially in the last, I'd say, 30 years, which is the study of these metric germs, usually either the outer or the inner metric germ, up to Bilipschitz homomorphisms. So this was pioneered by work of Pham and Teissier in the late 60s, for the case of curves. But then things got even more interesting with the work of Mostovsky, which proved for real algebraic germs that the Lipschitz classification gives rise to a discrete invariant. And the same result was extended to the complex analytic case by Paruzinski. So this is the reason that singularity theorists have been interested in Lipschitz geometry. And more recently, we've had the first results concerning a complete classification by Birber, Neumann, and Anpichon, who proved in 2014, who exhibited in 2014 a complete invariant for the inner Bilipschitz class of complex surfaces. Okay, and I will focus in this talk about complex surfaces, but first let me tell you something about the contents of the mini course. So as I said, there will be 3 parts. These 3 parts correspond roughly to 3 papers I wrote with André Bellotto and Anpichon. Actually, the third one is a third author, which is Andras Nemeti. And it appears that my co-authors have pulled rank on me, or maybe I drew the short stick, because I have to talk about the oldest paper. So it was a paper which came out on the archive on 2019 and was just accepted in Geometry and Topology this year, about the inner geometry of complex surfaces. So this is somehow old stuff. So I apologize for those of you who've seen this already. There will be a lot of repetition, but hopefully there will be a little bit for everyone, since I'm going to discuss a different proof of the main result. In the second part, which will be given by Anne tomorrow morning, she will focus on a very specific class of surfaces from the point of view of Lipschitz geometry, which is those the so-called Lipschitz normally embedded singularities, which are those for which the outer and inner metric are Bilipschitz. So she'll discuss results from our paper, but also previous results of hers and other people about criteria to give the special properties of these singularities and so on. And in the last part, Andrea on Friday afternoon will talk about an application of all this work to a problem we like to call the problem of polar explorations, which asks to determine the combinatorics, the geometry of the generic polar curve of a complex surface, starting from the datum of its topology. And this is this paper, this more recent paper with Andras Nemeti. If there's any words you don't know on the slides, don't worry, I will try to define everything. All right, so let me just start with the actual talk. I said I will focus on the case of surfaces and describe their inner metric structure. And I do this by means of an infinite family of invariants that were introduced in the seminal paper by Birber, Neumann, and Pichon in 2014 that I've cited before, which are called the inner rates and are defined as follows. So I have here my my singular germ x, 0, and I consider a good resolution of its singularities. So a good resolution, pi here, is a proper birational map from a smooth variety x pi, and I require that what I wrote here, E is the inverse image of 0 through pi, so it's the exceptional divisor. So pi is an isomorphism outside of E, and E is a straight normal crossing divisor. So in fact, for the rest of my talk, I will recite something more about pi, just to make my definitions and proofs a little bit simpler, which is that it factors through the Nash blowup and through the blowup of the maximal ideal. I will say a little bit more about this when I introduce this, these notions, but these hypotheses will not strictly needed, will not be strictly needed. It will just to make my life simpler. So this is my situation, and I have an exceptional divisor. And let me say E here is just one exceptional component, okay? So E is an exceptional component of the exceptional, it's an irreducible component of the exceptional divisor. And I define the inner rate as follows. I can take two curvettes on E, which means two smooth transverse curve germs on this component, here gamma and gamma prime. And I can push them to my singular germ, here pi star of gamma and pi star of gamma prime. And now I can define the inner rate of the divisor as the contact order between these two germs, curved germs on the right, with respect to the inner metric, which means what? It means that I take the intersection here of the germs with a small sphere. I consider the two intersections, and I look at the distance with respect to the inner metric. And now this distance, how does it go to zero as the radius goes to zero? Well, it's governed by a rational number here, which is called the inner rate of E, which only depends on the divisor E and not on the choice of two curvatures that pass through different points. So how should we think about this? We can think of this way. I can consider here NE is a small neighborhood of this exceptional component from which I remove the neighborhoods of the other ones. So it's a punctured tubular neighborhood of the component E. And when I push it on the right here, it gives me this slice here. And now the inner rate measures the size of this slice, meaning measures essentially how quickly this slice shrinks as I approach the singular point. Okay. And what's interesting here is that I can allow myself to for example, blow up points on this divisor and consider different good resolutions. It gives me a decomposition of the link in different slices, and I can take them as small as I like. Which means that if in principle I can understand all of the inner rates, this gives me a very fine understanding of the metric structure of the germ. I think it's a good point here to stop for a second and tell you something important, which is that here in this talk, I will not really be concerned with the Lipschitz geometry of this germ. So I will not consider the Lipschitz class, but I will really consider the metric germ itself, which is a finer invariant. Okay, so it's something which gives you a more precise understanding of the situation. And the Lipschitz geometry will really come back tomorrow in Anne's talk. But of course, I owe you an example. This is somehow abstract. So how do we compute this? I will try to explain everything through a very classical example, which is the singularity E8. So E8 is an hypersurface singularity in C3, defined by this equation: x squared plus y cubed plus x to the fifth, z to the fifth equals 0. I drew it a bit like I drew it before. How do I study this? And here there's a very simple method to study this kind of singularities by generic projections, which is due to Laufer and uses the study of Hirzebruch-Young singularity. And it goes this way. Here I can consider a projection. For example, I take the projection along the coordinates y and z, and this projection has a very convenient property for us, which is that it is generic in a reasonable sense, which is a bit hard to define. It's a tricky notion which was developed by Bernard Teissier. But essentially, we can think of this as saying it's something generic in the space of plane projection, and has good properties with respect to something that I will say in a minute. So I consider the generic projection, and what do I study attached to this projection? I consider its polar and discriminant curves. So what are those? Now assume that I put myself up here, looking down at the singularity. Okay, and assume that the singularity is somehow semi-transparent, made of glass or something. And then its polar curve, it's the place where the singularity bends from my point of view. Okay, so it's the ramification locus, to say it precisely, of this projection. So the polar curve is the ramification of this projection. The generic projection is finite. It's a finite morphism. There's a set of points where the number of preimages is different, which is this ramification locus, polar curve. And the discriminant curve, it's its projection. It's very clear from the equation that I'm looking at, when I try to compute the preimage of a point down here, I'm looking at the set of points where x squared is equal to this, meaning that in general, I have two solutions on the two sheets of this cover, but I have only one where y to the cube plus z to the fifth is equal to 0. So this down here, this is the equation of the discriminant curve. And up here I have its inverse image, it's the polar curve, okay? And now Laufer methods tell me how to describe a resolution of E8 starting from this data. And it goes as follows. So first I consider a good embedded resolution of the discriminant curve. So by this I mean that I replace C2 with a finite sequence of point blow up. So what I have here is a smooth surface I obtained by blowing up C2. And the 4 black curves I drew are the exceptional components. So I need to blow up the origin once, and then blow up a point there. And I do this a total of 4 times, and I create this chain of exceptional curves. And what I drew in blue is the strict transform of discriminant curve, which now became smooth and transverse to the divisor. What I drew up here is the dual graph to this sequence of blowups, meaning that I have 4 vertices, which correspond to the 4 exceptional components. And I have 3 edges. Every edge corresponds to a double point in the exceptional divisor. So whenever 2 components intersect, like this one and this one, the corresponding vertices are related by an edge. And I use a blue arrow here to denote that this component, this one, carries the strict transform of the discriminant curve. So this is the usual combinatorial notation. And what I drew here, like the rational numbers I put here, are the inner rates computing with respect to C2 here of these 4 components. So these are pretty simple to compute. Maybe I just say something in this very specific case. I have 1, which is the inner rates of the divisor obtained after blowing up once. And then I blow it up once more and I get 2. And these rational numbers here somehow interpolate between 2 and 1. I watch what I get when I blow up here. Maybe I have some time here. So I can just say, for example, this, I have 1 here and 2 here. And when I blow up, what I get in the middle, so is 1 over 1 and 2 over 1. What I get in this middle is 2 plus 1 over 1 plus 1, which is how middle school pupils sum fractions. We try to teach them not to, but then sometimes we do it all the same. And this kind of things appear when dealing with continuous fractions, which is not a coincidence. So these numbers can also be read from the continuous fraction development of this Puiseux exponent. So there's a whole description of this sequence of blowups that has to do with this Puiseux expansion of this curve. But enough about that. Now the magic of all of this, of Laufer's method, is that it explains me how to derive here the dual graph of a good resolution of this surface E8, starting from this data. And here I see that you have 4 components that correspond to the components that I have down here. I need to blow up once more and add components here. And I also blow up once more the point where the discriminant curve passes. But this, like, there is a very simple recipe. There's a cookbook for this in Laufer's book. And it's actually pretty simple and gives you this picture. And you'll notice that the inner rates here and here, they are the same. So this is the main way we knew at the time of Birber, Neumann, and Pichon to compute inner rates, was to use generic projections, compute the inner rate downstairs, and then lift it upstairs. The problem is that this is very complicated, as will be clear in a moment. Let me add something to the combinatorics of this picture, which is that I can also consider down here and up here a generic hyperplane section. Here I have an hyperplane to the origin. When I blow up, this becomes a smooth curve on the exceptional component I create with the first blow up. And I decorate this, the corresponding vertex with an arrow. I try to keep consistent the colors, blue for discriminant and polar curves, and red for hyperplane sections. And upstairs as well, I should have drawn one here. I have an hyperplane section, which I draw with a red arrow. So now the question is, how do I relate the two things I've been talking about, the red and blue arrows and the inner rays? More precisely, the fundamental questions that go back to Birber, Neumann, and Pichon are, how does the geometry of my singular germ influence the inner rays? And how can I compute them? So, and here's where the result of the first paper with Daniel Andre comes into play. Let me first give you a more naive statement, which is the following. So let me take a good resolution of X as before. And again, that factors to the blow-up of the maximal ideal and through the Nash transform. Now, maybe it's a good time to say something more about these two properties, because I've added polar curves and hyperplane sections to the mix. So I can relate the two. So the blow-up of the maximal ideal can also be thought of as the minimal birational map, such that the family of all hyperplane sections has no base point. And the Nash transform is the minimal birational map, such that the family of all generic polar curves, meaning the polar curves associated with all different generic plane projections, has no base points. But these hypotheses are here for a technical reason, to make this statement a bit simpler. Otherwise, I cannot really talk of red arrows and blue arrows, but I will give a more precise statement later, which does not need this hypothesis. Okay, so what's the statement? The statement is that the inner rates are in fact completely determined by the topology of X0. And now it's what's interesting to know, like probably most of you know this already, but the topology of X0 is equivalent to the datum of the dual graph, like this one. As soon as I add some weights to it, I need to weight it with the genera of all the exceptional components. In this case of E8, they are all rational curves. But for more general singularities, I may have ellipticals in there or not. And the Euler classes, the self-intersections of all components. So if I have this datum, I can reconstruct the link of the singularity due to work of Neumann, and therefore the full topological type of the link. So there are three data here that are equivalent to the datum of the inner rates: the topology, the red arrows, and the blue arrows. So I said here the inner rates are determined by this. In fact, if you give me the topology, the topology and the inner rates on the graph are equivalent to the datum of the graph and the two arrows. So I will give, this is the naive, the more qualitative version of the theorem. I will give a precise formula in a moment, and it's just some more definition. But first, other questions about this first statement and all the definition. I understand it's a bit dense. All right, so let me move on to the precise statement. I will actually give only one theorem in this talk, but I state it several times in different forms. So to give the precise formula, I also add some more data to the dual graph, in this case of E8, in general of my singularity, which is a metric which is naturally attached to it, as follows. Whenever I have two vertices which are adjacent, like this one and this one, I can consider, so remember, a vertex is associated with an exceptional component, EV, in pi minus 1 of 0, while inside pi minus 1 of 0, this component comes naturally with a multiplicity. And this multiplicity is denoted by MV. Another way to see this multiplicity is by taking a generic hyperplane section, pulling it back to the resolution, and look with multiplicity this section vanishes along the component. And then I define the length of this edge to be 1 over the product of the multiplicity. In this case, 1 over 8. So this gives me a natural metric on the graph, which has a nice topological interpretation that I will discuss later. So here I have my graph, my inner rates on the vertices, these lengths, the blue arrows, and the red arrows. And they also have, remember, the weights coming, I mean, the self-intersections and the general. So something, well, second to last definition before giving the statement. What's interesting about this is that now I can see the inner rate function as I can extend it by continuity, by linearity inside the graph. And I can think of it as a piecewise linear function on the metric space underlying the graph. And then it becomes, what's interesting, that it becomes a function with integer slopes. Here in the case of E8, I took a neighborhood of this vertex here, and I drew the slopes here. The slopes have, with respect to this vertex, there's an ingoing slope, there's an ingoing edge along which the inner rate has slope 2, an outgoing edge with slope 2, and an outgoing edge with slope 6. And then I call Laplacian of the inner rate function on this graph at the vertex V, the sum of all outgoing slopes. So in this case, I have 6 plus 2, and there you have 2 incoming, which means minus 2 outgoing. And so the Laplacian is 6. So I have this datum somehow keeps track of the inner rates. I have the blue arrows and the red arrows, and the topology is encoded by one last definition, which is a definition which is fairly standard in graph theory, which is the canonical divisor of the graph, which attaches to every vertex an integer, and this integer is the valency of the vertex, meaning the number of edges adjacent to it, 3 in this case, plus twice the genus of the component, minus 2. So this, if this tells you something, it's because topologically this is nothing else than the opposite of the Euler characteristic of the exceptional component from which I remove the intersection with the other components, I mean the reduced space. I forget its multiplicity. And now the precise version of our theorem is what we call the Laplacian formula, because it's a precise formula for this Laplacian here. So you have the Laplacian here, which is equal to the multiplicity times the canonical divisor, which keeps track of the topology here, twice the number of red arrows at the vertex V, minus the number of blue arrows. So you have the 3 ingredients here on the right-hand side, and one on the left. So a few comments about this. So let me keep this statement on the slide. Why do we care about this weird combinatorial object? And the reason I care about it is because it allows me to determine completely the inner rate. Remember, as I said, if I know all of the inner rates, I have a very fine understanding of the structure of the graph. So this is for 2 reasons. The first reason is that the inner rate takes, like, the minimum of the inner rate is 1, and in fact it always takes the value 1. As in the example of E8, remember we had inner rate 1 at every point carrying a red arrow, and this is the case in general. So 1 where there is a red arrow. So the minimum is 1 and is attained, and the Laplacian of a continuous piecewise linear function, it determines up to an additive constant. And I like very much the following proof of this simple fact, so I'm going to give it to you. So the Laplacian it's pretty simple to see that the Laplacian is a linear map, and therefore it's sufficient to prove that if a continuous piecewise linear function has Laplacian 0, then the function is constant. Then by the first part, I will be done. And for this, I can suppose by contradiction that I have a piecewise linear function which has Laplacian 0 but is non-constant. This means that there is one edge along which the Laplacian function grows. So let me draw somehow the graph of the Laplacian here. Okay. Now, here I can look at the Laplacian of this vertex. This might have several edges attached to it. But since there is a non-zero incoming slope, and the Laplacian must be 0, there must be a non-zero outgoing slope somewhere, say here. Now I can draw the inner rate function here goes up. And now I can repeat this argument here. And I can keep repeating this argument. And what happens is that at some point, I will run out of vertices because the graph is finite. And therefore, this argument should, like this, I should close a loop. I walk on the graph down here. I walk on the graph, and at every step, the inner rate goes up. But at the end, I'm supposed to close down the loop. And of course, we see that this is not possible. So I like to think of this proof this way. So this is a Penrose staircase here in a very well-known lithography by Maurice Cornelius Escher. But you know that in the real life, this does not exist, and therefore proves that the Laplacian of a continuous piecewise linear function determines it up to an additive constant. All right, so let me say something about the original proof we gave in our 2019 paper of this result. Because this proof was very topological. So the idea was to first study the formula in this mood case for C2, which is fairly simple. You just need to understand what happens to inner rates under blow-up, essentially. And then use a generic projection to lift it very carefully to the singular germ. And this is very delicate because it requires to keep track of very fine properties of the Milnor fiber of a generic linear form, its topology, and its monodromy. And I mentioned that the metrics before, the metric on the graph has a nice interpretation in terms of topology, while it's in terms of the then twist of the annuli in the link corresponding to the double point, for those who know what these are. But today I wanted to give you something new, which is a new proof, which is fairly different, and it's due to Yanni Cherek, who's a PhD student of Anna and André. And his proof makes use of differential forms, of the fact that I can relate essentially all the ingredients I have here somehow to differential forms of my singular germ. And then this formula will come out of the adjunction formula. So I will give this proof in a moment. Let me just say that there's also a more arithmetic version of this approach, which was studied by Baker and Nikese in the context of the study of Laplacian of weight functions on curves over discrete valuation lengths. So for those of you who know this, great. For the others, you can forget it. But this approach does not originate with complex singularities. Just so you know. So what the relation with two forms? It's the following. I said that we study inner rates by studying generic projections. And here, when I have such a generic projection L, I can take, say I take coordinates X and Y, Z1 and Z2 downstairs. I can take the standard volume form dZ1, watch dZ2 here, and I can pull it back to X. And this somehow gives me, a two form on X, which is itself somehow generic. So the precise way to do this is to say this gives me a generic element of the zeroth fitting ideal well, I should have said also what this pi was, but this works regardless of pi. So I also take a good resolution here. And again, let me ask this good resolution factors through the Nash transform of this map. Now, when I pull this back, if this projection is generic with respect to pi as well, this gives me a generic element of the zeroth fitting ideal of this. So it's a very nice two form on this singular space. And now to retrieve all my invariants, I need to do careful local computation inside the singularity as follows. So here I have this all these exceptional components, a EV, and I take a free point here, so a simple point, not a double point, the exceptional divisor lying on the component V. And I can find local coordinates. So around this point, this is smooth. So I have two coordinates X and Y, such that the divisor EV is defined by the first one. And if I pull back this to form, which came from C2, I can write it in this nice way. So I have dx wedge dy times the Jacobian of this composition of pi with L. I can write it another way as follows. I have x. So the exceptional component will come up with some multiplicity, which now here I denote kv hat log, times a function f of xy, which does not vanish along the divisor EV, times dx wedge dy. Here, for technical reason, it's better to use logarithmic coordinates. So I put one extra x here at the denominator. So this somehow, this kv is not the order of vanishing of the differential form omega, it's the order of vanishing plus one. And in fact, this invariant has been studied before in birational geometry, and it's called the mother log discrepancy of E. Now I use the W here, but since as I said, this W is a generic element, this gives me the same as the order of the fitting ideal plus one. And now to connect it what I know, we have two important facts. The first is that I can retrieve the inner rates by this simple formula using the multiplicity and the mother log discrepancy. It is a local computation in the singularities, in the resolution, sorry. And then that this function f is precisely a local equation for the strict transform of the polar curve. So the red arrows. So in a way, this differential form does not quite behave as the polar curve, meaning that it might have a different order of vanishing along the exceptional divisor, but outside the exceptional divisor, the strict transform is the same. And this is what I need in my proof that I will give now. So here's my statements again. Let me start by first writing down the Laplacian. So the Laplacian is the sum of the outgoing slopes, meaning that if I have V and V prime here, the outgoing slope is I of V prime minus I of V over the distance between V and V prime. Now the distance is 1 over MV and V prime. This IV is the mother log discrepancy plus 1 over, sorry, of that because I put the log over MV plus 1. If I plug this in, I get this formula for the Laplacian. And now if I use the second part, it tells me that when I intersect the divisor given by the differential form or by the two ideal, which is the divisor whose coefficients are the mother log discrepancy, and I also have the strict transform. Since I know that the strict transform is the same as the polar curve, this gives me the strict transform of the polar curve here, which means that in this intersection theory computation, I get the number of hyperplane arrows, of polar arrows. Sorry, this is blue. I don't know if this works. Yes, so these are blue arrows. Now I plug this in together. Here I have this sum of the kV prime, and here I have a sum of the kV prime. So I take this and plug it in there, and I start getting something which resembles my formula. I have the Laplacian here on the left, something, and the polar arrows on the right. Now I can look at this something in the middle, And this something in the middle is simple. It just, well, kv hat log times this guy, and this guy is the intersection of the component EV with the all the exceptional divisor. So this gives me precisely, this exceptional divisor is given by the multiplicity of a generic hyperplane section. So this gives me precisely the strict transform of the hyperplane section. And now there's a small trick here, which is that wherever I have hyperplane sections, the inner rate was 1, and so the kv log is 2mv. So this is either 0 or 2mv. I mean, it's always 2mv because if kv is not 2m, then L is 0. So in the middle here, I found LV, and then all that's left is the middle, is this part here, and this is what's given to me by the adjunction formula. So the canonical, sorry, the log mother divisor, the mother divisor is numerically equivalent to the usual canonical divisor, which lets me get precisely the canonical of the graph, and we are done here. So I think I'm out of time. Let me just put on the board something else. So first I want to say that Cheryk's theorem, I believe, is well, part of a larger work in progress, which is much more general. The one I know about is an analogous formula for generalized inner rates attached to more general finite morphism than generic projections. But I think there's much more to come, so you should ask him. And then I also wanted to put on the board a more effective version of this formula, which is equivalent to the previous one, which is, I believe, what Anne and Andre will use explicitly in their talk. And let me also mention that among the various applications of this formula, one of the things we get is that this gives strong restrictions on the relative positions on the blue and red arrows, which is something that Anne and Andre will come back to in the rest of the minute. So I'm out of time, so thank you for your attention and your patience.
Thank you very much, Lorenzo. Any questions? I have a question. Did you define the fitting ideal of the map pi, or did I miss it?
I did not. So it's essentially defined by, well, one way of doing it is by embedding the germ in a smooth germ and look at all two forms in this smooth germ and restrict them to the surface. And then essentially, I mean, with respect to the map pi, what's going on is that I want to avoid this the differential form which have too high vanishing order along the components of the exceptional divisors. So it's essentially in the same way as when I said generic projections, sometimes I took for granted that what I meant was generic also with respect to a resolution, which means that, for example, if I look at the if I look at the polar curve of this generic projection, I want it to behave as all the others. So I don't want to blow up, for example, the point where this passes.
Okay. Okay. Any more questions from anybody? No. If not, we thank Lorenzo again.
Thank you.
We'll go on until until 11. Yeah. Thank you, Lorenzo.
You're welcome. Well, thank you for coming and for the invitation.
Can you hear me? Just let me make sure. Lorenzo.
Yes, we hear you.
Perfect. So our second lecture this morning is Antoni Rangachev, who will speak about the algebraic theory of continuity for meromorphic functions.
Okay. Well, it's nice to be here. It's the first time I give a whiteboard talk in a year. So let's hope we'll be able to do this more often in the coming months and years. So my first talk will be quite basic, and pretty much everything I'm going to say, it's well known. But this is a part of a 2-series course. So this first part is a very expository one. So let me fix some notation. X is a complex analytic variety. By M of X, I will denote meromorphic functions. And by S of X, I will denote the singular locus of X. If there is a problem with the display of my handwriting, please let me know. There is some light coming from the lights here. There is some reflection, so there might be some issues, but yeah, let me know. And yeah, well, f is a meromorphic function. So what I'm going to talk about today, very briefly, of course, is about this dictionary between analysis and algebra. So here we have, maybe I'll write it here, table analysis one side and algebra on the other side. So if I consider those f that are locally bounded at S of X, so that corresponds. So what does this locally bounded mean? It means that you take a small neighborhood, at a point, and you exclude the singular locus, and you ask f to be bounded there. So this locally boundedness condition, it translates into algebra. Well, f is in the integral closure or the normalization. By the way, I'll be always looking here, so you can, if you feel comfortable with this, we can assume that x is irreducible, and I'll be working pretty much the entire talk will be locally at a point. So f is in the integral closure, or this is described by an algebraic relation of this form. The AIs are holomorphic functions. Okay, so this is classical, as we're going to see. This is Riemann's extension. Well, it's pretty much embedded in Riemann's extension theorem and the theorem for the primitive element. So we're going to discuss this. So, but then we can look at those f that are continuous, and there is an algebraic object called the semi-normalization. I'll abbreviate it by SN here. It's not that easy to describe algebraically. I'll just give one description, which is kind of curious due to Swan. Swan characterizes it in the following way. So whenever b cubed is equal to c squared for b and c in this object, the semi-normalization, there exists a such that c is equal to a squared, c is equal to a cubed. Okay, so this continuous F, they form a sheaf called the semi-normalization. It was first, I think, considered by Andriotti and Bombieri, and more recently it appears in the work of Koller and Kovac in the minimal model problem. And so you can go further and let's say consider not simply continuous, but some sort of strong continuity. You can consider Hölder continuity. So this is exactly the notion, the familiar notion from calculus.
Tony, excuse me. So where is A when you write B equals A square, C equals A to the cube? And what is F with respect to B and C? What does it mean?
So F with respect to, well, A is, yeah, so whenever you have two elements B and C in the semi-normalization satisfying this property B cubed equals C squared, there exists another element A such that B is equal to A squared, C is equal to A cubed. This is kind of an algebraic description of semi-normal rings.
A is in the semi-normal ring.
Yeah, A is in the semi-normal ring. And there was another question, Anne. I couldn't hear it well. Can you repeat it?
No, it's okay. Thank you. Thank you.
Tony, can I interrupt?
Yeah.
If you look at x cross x, and you look at f tensor 1 minus 1 tensor f,
yeah.
If it belongs to the root, the radical of the diagonal ideal, then the function is continuous.
That's right. Ah, yeah. Okay. So exactly. Yeah. I think we discussed this. So perhaps this is
more intuitive,
a better way, and it will come here naturally in the discussion about this continuity. But I didn't want to bring up this dictionary yet. Yeah, it will come up. But yeah, Bernard is right. There is a better way to phrase a better test for a function to be in the semi-normalization. So we have a Hölder continuity, and I will describe this. So this is essentially in the work of Pham and Teissier, slight modifications, very slight modification of their work. So this PQ corresponds to the Hölder exponent. So Hölder exponent alpha equals PQ. Of course, the interesting exponents are between 0 and 1, right? So if it's alpha is greater than 1, like a function satisfying the Hölder inequality with such exponent is a constant. So these are not interesting. So here, these are characterized by satisfying the Hölder inequality. And so for the case P equals Q equals 1, this is of course the Lipschitz saturation hence introduced by Pham and Teissier. There is a recent translation of their work, which is available from Bernard's website, the translation in English. What we're going to do today is just modify a little bit their work, introducing an algebraic, familiar algebraic object to do this more general, slightly more general definition. Okay, so this is the dictionary. And the purpose of my talk today is very briefly to describe this correspondence between inequalities and algebra. So I'm going to start here with the Riemann's extension theorem, and then we're going to jump here. So this part with the semi-normalization we're going to skip today. But yeah, one can, as Bernard pointed out, it can be incorporated in this discussion of Hölder or Lipschitz continuity quite easily. Okay, so OXPQ. These are all meromorphic functions satisfying.
Okay.
Yeah.
You just added this alter.
Yeah. So if I pull it like that, that disappears, right? So you cannot see it. Well, life is not ideal. In the okay. So I don't move this.
Let's be.
Yeah. Okay. I erase. Okay. So what is the first Riemann extension theorem? So all the proofs I'm going to give today are really sketches. So I'm going to miss lots of technical details, choice of neighborhoods, and all that. I'm just going to jump right to the main idea because of time constraints. So A is well, D is a domain in Cn. So D is a domain, and A is nowhere dense analytic set in D. Okay, and then the claim is every holomorphic function f in D minus A, which is bounded near D minus A has a unique holomorphic extension f hat to D. Okay, well, this is quite simple. So again, I'm skipping some details. So here is a sketch. So I'll be working in some neighborhood U, well, D minus the singular locus of A. So it's based on the dimension of A. So first cases are trivial. So now the conclusion, well, the observation here is that I can look at points away from the singular locus, because if I'm on the singular locus, it's analytic and it's of dimension strictly less than the dimension of A. So, and then we run the induction hypothesis. So this is nice that we can work away from the singular locus because we can choose coordinates. So I'm going to choose some coordinates Z1 to Zn. And I'm going to work now in U minus the variety of Z1. So then we can write F. We have a uniform Laurent series expansion for F. So F of Z, I'll write it as so Z prime. I'll define what this Z prime is. So Z prime is just the coordinate Z2 to Z. Okay, so this is of course, so here, this, well, let me erase this. This AI is so holomorphic in a small enough neighborhood around the origin. Okay, so I can compute these AIs by Cauchy's integral formula. So we have that this AI of Z prime, I can compute them. So for small enough So I'll be working with some, small enough radius zeta of, well, small enough radius epsilon. So this is this is not a good notation. Let's use K because we have the imaginary unit with I. So you see what happens here is that when K is negative, when K is negative, and given that f of zeta is bounded, this is bounded. Yeah.
In your sum, f of z, it's z power I or z1 power I?
Z1.
Here?
It's z1 power I.
I see, of course, I'm sorry. Thank you. Yeah.
Thank you.
Yeah. Okay. So, because this is bounded, you see, this is bounded, this guy is going to jump in the numerator when K is negative, and by letting this epsilon approach 0, this will imply the vanishing of all these guys. And so this is 0 for K negative, and you get a Hartog series. So all the negative coefficients vanish, and by this, you get only things in for K or for I greater or equal than 0, and from there you immediately see that this gives you a holomorphic extension f hat to D. So this is all, I cannot do this. So this is all classical. Now, how do we do? Let's quickly establish the version, the more general version of this theorem. So of course, let me remark here that I can replace this. It's clear that I can replace this D by a complex manifold. And I can work with a analytic set in this complex manifold. This is trivial. Now, I would like to further relax this complex manifold. I want now to get a version of this theorem allowing singularities. So I would like now to replace this complex manifold with a complex analytic variety. This gives us, well, Riemann extension theorem, I guess, 2. Okay. Which is, well, we'll see, it's one applies some algebra, basic Galois theory, like or the primitive element theorem to reduce it to the Riemann extension theorem 1. Okay, so X is reduced complex analytic variety, or squares. I'm sorry, space. A is a complex subspace. And F is holomorphic. On X minus A and bounded near A. Can you read what I'm writing, because I don't think I can do that anymore. So maybe I switch with okay. Yeah, this is better. So which is bounded near A. So then the claim is that then F has a unique meromorphic extension F hat, which in fact belongs to the normalization. Okay, so how, like I don't want to get into details, but let me just give you the idea of the proof. of the second version, a more general version of the theorem. Well, I should say that this part of my talk, a good references are there are two books that the theory is well explained, in my opinion. It's Grauel and Remmer's book and Narasimhan's book. They both do a very efficient job at explaining these classical results. So, of course, we want to reduce to the first extension theorem. So we take a sheeted, we realize X as a sheeted covering over, let's say, a connected domain is Cn, the same dimension as X. Yeah, so this is a B-sheeted covering. So we want to push down everything here, and we know what happens here. Here we have Riemann's extension theorem. So how does this work? Well, there is some algebra involved here, which, like the details of which I'm going to skip. So you can realize this, sheaves in the following. Well, we really work always locally at the point, but yeah, in this way. So I'll explain what this is. So G is a primitive element. It's what you use to get when you look at the corresponding field of fractions. Well, this is a finite field extension of this one, well, the smaller field, and you can get it by adjoining one single primitive element. And delta, it's what's called the universal denominator. You can simply take it. So if H is the characteristic polynomial, is the characteristic, let's say H sub Z is the characteristic polynomial G. Okay, so this is a polynomial in all y of Z. Then, well, if you take the derivative of H and you evaluate it at G, this gives you this universal denominator. It's not a canonical choice, but this is how you can construct this universal denominator. The property of these universal denominators now is, in fact, one can show that even the normalization is here between these two guys. Well, of course, it's not allowed. But from here, one can show that delta times F. So delta times F, so if I apply delta to F, so F, one can show that it sits somewhere in between. If I apply delta to it, I land with a function in O of y. So this is, in fact, it's a polynomial with respect to G. And of course, it's in degree b minus 1. B is the degree of this covering. So here these CIs, they are holomorphic functions in O sub y minus the image of A. So what happens is that you multiply F by some delta in O of X. That's so this universal denominator, and you get this kind of expression. So this is, in fact, some simple linear algebra to derive this. But now you see this is on Y. Y is smooth. The boundedness condition of F translates to a boundedness condition on all these C of I's at the image of A. Okay? So by applying Riemann extension, by applying the Riemann's extension theorem 1 to this CIs, and so I should say boundedness of F translates to boundedness Ci, and then by Riemann 1, Riemann extension theorem 1, the Ci extend to holomorphic functions. Holomorphic functions Ci hat, which are in O of Y. Okay.
So delta is, what is delta? Delta is a universal
Denominator. Denominator.
Okay, yeah, I read this, which is what exactly it's universal.
Well, yeah, this is this is. I mean, it's kind of it's a common. Yeah, it's a common denominator. This is what it tells you that you can do. Yeah. And this is a way to construct it, but yeah, this is. Yeah. I mean, I'm skipping here some linear algebra, and of course the primitive element theorem. So okay, so this is, you multiply by some delta, and you get a function that you can extend to a holomorphic function on the entire y. So how do we see that in fact this gives rise to a meromorphic function f hat, which belongs to the normalization? Well, so I'm going to consider now this sheaf OX WH. This WH stands for weakly holomorphic. That's another way to call this function, these locally bounded functions near A. So these are OF. Yeah, so I will do it. Let's just assume that I'm interested in the singular locus. This is my, okay, so locally bounded near S of X. So what you do is you take this delta, so to each F, you associate this delta F. Okay, you associate this delta F. So here I think I have a, wait a second. So this is, I'm sorry, so there's something about that. Okay. So what happens is, okay, so first you show that, okay, you can show that this is an algebra, forms an algebra, and then you have a map from here to here. So this is, and this belongs to O of X. So this map is injective. This map is injective, and then what's the image of this map? Let's call this map phi. So the image of phi is an ideal. It's an ideal. It's an ideal in O of X, which is Noetherian. Okay, so this is how you show. Well, it's an ideal. So you can, each ideal is a finitely generated OX module. So you can show that this OX WX is a finitely. So therefore, this thing is a finite OX module, and this is again, maybe it's what is it, the determinantal trilemma. This tells us immediately that this set belongs to the integral closure. Set belongs to the integral closure. Therefore, well, algebra of weakly holomorphic functions, it belongs to the integral closure. So now I want to establish that the integral closure, all elements here, all meromorphic functions that are integral over O of x, in fact, they correspond to this locally bounded function set S of x. So this follows easily from, so if you take, so conversely, let f be a function from the integral from the normalization. So then you can write an equation of integral dependence, and using by the triangle inequality, now you apply norms. So by the triangle inequality, what you get is, I think it's the minimum here. Well, I'm sorry, f is less than the maximum. Okay, so this is how you get the boundedness condition, and this establishes this relationship between these locally bounded functions and the meromorphic functions that satisfy an integral dependence relation. So this was a crash course on Riemann's extension theorem. All the details are in the books that I mentioned. So now that we establish our first connection in the dictionary, I want to move to the other connections, and of course they're all based on this. But we need a new technical device. We need the integral closure of ideals. So we go now to some classical work of many people. But I'm going to here follow the exposition that's given in Bernard's and Monique's lecture notes on the integral closure of ideals, which are again available on Bernard's website. Okay. So, I mean, I'll state it as a theorem, so it's a theorem slash definition. So this is a reference. So X is reduced, again, complex analytic. And I is an ideal in the local ring of functions at the point X. And F is an element from this local ring. And we have these two equivalent conditions. Well, F is in the integral closure of the ideal I. What this means is that F satisfies such an integral dependence relation. So these AIs belong to the I power of the ideal I. And the other condition is, so this is an algebraic condition. The other condition is an analytic condition. So for each set of generators, of I, for each set of generators of I, there exists a neighborhood U and a constant C. Well, those depend on F and the set of generators of I. So I'll denote these generators by G1, GS. We have the following inequality. F of X is bounded by the supremum, or well, C times the supremum G I of X. I is from 1 to S.
Sorry, Tony, maybe here the indices, you want to say A1 to AK minus 1. Because you put
yes. Thank you. Okay, so it's this analytic inequality translates to this integral dependence relation, So I'm not going to give a proof of this because we don't have time. And let me just describe to you very briefly what's the connection with this theorem and what I just did with this Riemann extension theorem. So to see that 1 implies 2, this is, I mean, you can see that this is kind of the easy part, which follows by, again, some sort of triangle inequality. So the hard part, I think, is to prove that 2 implies 1. How do we get this integral dependence relation from the inequalities? Well, we already saw something like this with the Riemann's extension theorem, the second version. Yeah, so if I can turn this inequality into a boundedness condition, then maybe I can translate it into an integral dependence relation as we did there. So to do this, you need to consider the blow-up. And so let's say we look at some affine chart for the blow-up, such that this ideal, let's say that this ideal, the fullback of I is, so let's say it's generated by one of these generated G1. I mean, it's principal, so it's a linear algebra statement to see that it has to be generated by one of these generators. And then one can see that this inequality translates into this kind of condition. So that this is bounded. Okay, so, well, from here, one gets that, therefore, this is integral over here, over all of B sub alpha. Again, to get this, this is in fact, yeah, this is Riemann's extension theorem too. And so once one can see this, I mean, the way Bernard and Monique are doing it, it's through the normalization. They take the normalization to begin with. One can do it also in this way to get an integral dependence condition for f of this sort. But this is, yeah, this is the idea. Okay, so now in the remaining 1 minute or 2 minutes, I'll just define the notion of rational powers of ideals, which will help me to define the Hilder saturation next time. And we'll look at an application of this theory. So let me erase here. So in order to capture the Lipschitz and more generally the Hilder inequality, yeah, we're going to do this through integral closures of ideals, but to do this more generally for Hilder exponents, I need to introduce the notion of rational power of ideals. This brings me to this purely algebraic topic, rational powers of ideals. Well, I think there is a reference in one of Bernard's works on this, maybe on some Lipschitz exponents, or
it's in the same.
Or it's in the same, or maybe it's at the end, towards the end. Yeah, it's in the same lecture notes. Another reference that you can look up is in Svansen's and Pooneh's book on integral closure of rings, ideals, and modules. I think it's section 10.5. So this is discussed also there. So what is this notion? So I'm going to work with a ring R, commutative with identity. It doesn't have to be Noetherian to begin with, but let's assume it's Noetherian. We're only interested here in Noetherian rings. I is an ideal. Alpha will be a rational number. Yeah. And then I define this rational power I sub alpha as all elements in the ring R such that x to the q belongs to the integral closure of the p power of r. Okay? So you can check that this is an ideal. It's kind of a trivial exercise to do that. So I'm going to skip it. So let me just briefly mention some basic properties of these rational powers. So here are some properties. So properties. Well, if alpha is greater than beta, I sub beta is contained in I sub alpha. So we have I sub alpha times I sub beta. So this is product of ideals is contained in I sub alpha plus beta. What else? I sub alpha is integrally closed. It's an integrally closed ideal. And finally, if alpha is equal to n, a natural number, then I sub alpha is equal to the integral closure of the n power of I. Okay, so one more property and I'm done. So for each idea, we can associate the Rees valuations. So these are Rees valuations. So these are the valuations that determine the integral closure of the various powers of the ideal I. In fact, assume that we work over a domain. R is a domain, just for simplicity. Then we have this result due to Rees. Well, these are unique. And we have this decomposition. So for kind of a modern treatment of this result, you can also look at my paper on evaluation theorem for Noetherian rings, where this is proved in a more general setting. Anyway, so these VIs, they determine the integral closure, and I'm going to set, V sub I for evaluation capital B. This is some integer. It's the minimum of the x, where x runs to I. Okay, so these are discrete valuation rings. So this is non-zero, non-negative. I'm sorry. So then the statement is. Then, so I'm going to look at this E, it's the least common multiple of all these numbers, integers here, and then the statement is that, it's some basic valuation theorem. For each alpha rational, you can express, there exists an n natural number such that this rational power of I is equal to I n divided by E. Okay, so we have a common denominator, so to speak, always, that depends on these valuations, and each such I sub alpha is of this form. And I'm going to stop here. So this is the algebra we need to analyze the Hölder property, and I'm going to continue with this next time. I'm going to prove a basic property. for the sheaf of Hyoder continuous functions, prove that it's a coherent sheaf locally at a point. And we're going to look at an application to quasi-ordinary singularities, and that will be tomorrow. Thank you. Thank you.
Questions?
Maybe because this is a bit sketchy. Do you mean here that VI are the valuation rings?
Yeah, the capital ones are the valuation rings. Well,
Okay, because you say, and maybe you can say what are these valuations. So these valuations, you blow up, you take the
normalization. Yeah,
blowing up.
yeah, and yeah, I mean there is a way there you look at certain localizations at height 1 prime ideals there, which gives you these discrete valuation rings.
Okay.
It's precisely where the morphism from the normalization to X jumps, so the fiber dimension jumps. So it corresponds to some height 1 prime ideals. And
yeah, which means the reducible components of the exceptional divisor of the
exactly. Yeah. Or exactly. Yeah.
Just a comment, when you wrote alpha less than beta, what you mean to say is if alpha is greater than beta, then I alpha is contained in I beta. You just reverse the.
I reverse it? So
that's okay.
Okay. Okay. Yeah, thanks.
Any other questions or comments? Then we thank Pooneh again. John.
Yeah.
Ooh, this is a infinite perspective.
Yeah.
Wow.
Okay. It's my pleasure to introduce Thierry De Pauw from East China National University and University of Paris, who will talk about linear isoperimetric inequality for normal and integral currents in compact subanalytic sets.
Thank you very much. Can you hear me?
Yes. Yes.
Great. So thanks very much to the organizers for inviting me to contribute a talk to this conference. I'm actually very honored to be part of this. And as it is sort of at the intersection of two subjects, I will try to introduce all the relevant vocabulary, but please interrupt me when something is not clear. So let's start to recall what the isoperimetric inequality is. If S is some region in the plane, then its area is bounded by a constant times the length of its boundary to the power 2. And here the constant, the optimal constant, of course, is known, and it corresponds to the case of a round Euclidean disk, the case of equality. Now, let's talk about the terms here. Area can be understood as the Lebesgue measure, and length can be understood as the one-dimensional Hausdorff measure of the topological boundary of S. So actually, if this number is finite, this says something about S. It says that it's a set of finite perimeter, or equivalently, the indicator function of S is of bounded variation. If we want to be a little bit more precise, we should have a definition of boundary that does not change when we change the set S by a set of measure 0. So we'll not go into these details, but it's just to indicate what's the natural setting for stating this kind of inequality. This holds also in higher dimensions. So if S is a set in Rn+1, say it's Lebesgue measurable, then its Lebesgue measure is bounded by the codimension 1 Hausdorff measure of the boundary of that set. And then, of course, again, to a power here that's a Euclidean power. So when I talk about Euclidean isoperimetric inequality, I refer to this power here. So how about higher codimensions? Then the proper domains for stating this sort of thing, isoperimetric inequalities, are perhaps the integral currents that were introduced in 1960 by Federer and Fleming. So I will say a word in a few minutes about what these objects are. For now, you can think of simply pieces of surfaces of the right dimension, so submanifolds, for instance. So let K and N be integers, and that satisfy this pair of inequality here. Then there exists a constant with the following property. Each time we are given some S naught, K plus 1 dimensional in Rn. Now the bold I here is for integral current, right? So we will say what that is later. Each time we're given a K plus 1 dimension S naught, there is another one with same boundary and whose mass is controlled by the mass of the boundary, again, to a power here. So this is the isoperimetric inequality in higher codimensions. Now the constant in the proof of Federer-Fleming depends both on K, which we expect, and also N, which we don't expect. And in fact, they didn't really have a good estimate in their proof. Almgren in 1986 proved that the constant depends only on K, the dimension of the surfaces, and the equality cases correspond to S being a K plus 1 dimensional flat disk. So this is what we expect, and the constant is again known in that case. So how about we change a little bit the ambient space? So here we've discussed only Euclidean spaces as ambient spaces, but we could think of other stuff, perhaps manifolds with singularities. Okay, so Gromov in 1983, and then following up on that, Wenger in 2005, they established Euclidean isoperimetric inequalities, so with these powers, again with constant depending only on K as well, in different cases. So for instance, the ambient space is a finite dimensional norm space in Gromov's work, or a infinite dimensional Banach space in Wenger's work, or a complete Riemannian manifold with some cone type inequality in Gromov's work, or, and I want to mention this, simply connected metric spaces with non-positive Alexandrov curvature. So that's a condition on curvature. We'll come back on this in a minute. So we can also change the ambient space for a compact Riemannian manifold. So in case A is like that, there is a constant again with this same property. So I state it again, for every K plus 1 dimensional S naught, integral current of dimension K plus 1, there is another one of the same type with the same boundary, and the mass of S is controlled by that constant times the mass of boundary S, again to that same power here. So in other words, everything works fine in this case of smooth compact Riemannian manifolds. So now what happens in case we try to introduce some singularities in the ambient space? So here is what happens. So for instance, we want to replace Riemannian manifolds with real algebraic varieties. Why not? So the first thing to look at is a cusp. So n is an integer, 2, 3, 4, whatever. And we look at this simple cusp illustrated below, the set capital A sub n. And in that set, we consider a circle. So TH, that's an oriented circle. We can see there's an integral current. We will see this soon. It's at height h, so it's of radius r with obviously a relation between r and h, and so its mass, which is the length of that circle, is easily computed. Now, that circle bounds a unique disk, two-dimensional disk in the cusp. It's S sub h. And S sub h I can also see as an integral current. We'll see this in a second. So S sub h has some area that can be explicitly computed. So if I want to consider isoperimetric inequality, I'm going to look at this quotient here, this ratio of the area of the disk, SH, the surface, and then in the denominator, the length of the circle to a certain power, right? And it's easily seen that no matter what constant q here, no matter what power q I choose, I can choose an n so that n plus 1 over n is slightly less than q. And then in that case, this thing here will actually tend to infinity when you let h goes to 0. So that means you look at these circles going down there, right? So that's a cusp. So the density is 0 of area there. That's what it means. And there is no hope, of course, for an isoperimetric inequality with an exponent, a power on the right member of the inequality that would be strictly larger than 1. So that would work for every, say, real algebraic variety. Okay, so here is the theorem with Bob Hart. So we consider a compact subanalytic set A, and with that set there is associated a constant with the following property. Again, if S naught is a k plus 1 dimensional integral current supported in A, right, lives in A, then there exists another one with the same boundary and whose mass is lesser than or equal that constant times the mass of S, but now here there is no power, there is the power 1, right? We've seen in the previous slide that we cannot hope for anything else if we want the constant here to be the same for every compact subanalytic sets. Of course, maybe situation is different if we have a constant depending on the set. So there's a related recent preprint by Anna Valette and Guillaume Valette, Poincaré inequalities on subanalytic sets. And that is about functions. It's not about sets, but of course, isoperimetric inequalities and functional inequalities are related. So that would be related to the case when A is a top dimensional set in Rn, and also the currents are top dimensional as well. So let me now spend some time reviewing integral currents. So integral currents are kind of the opposite world of subanalytic sets or algebraic sets, which are, you know, moderate and always finitely many pieces. So integral currents are sort of the opposite. They serve purpose in the calculus of variation, and they may have infinitely many pieces. So first of all, this notation, dm here, is for the space of smooth, compactly supported differential forms of degree m. So for instance, if m equals 0, these are the test functions of distribution theory. So of course, that space comes with an appropriate topology. And the corresponding dual space is the space of m-dimensional currents in the sense of Georges de Rham. So when m is greater than or equal to 1, there is a boundary operator defined. It sends m-dimensional currents to m-1 dimensional ones, and it is defined to be the adjoint of exterior differentiation. Of course, that definition is justified by the Stokes-Cartan theorem. Can we map currents? Well, yes, if F is a smooth, C infinity smooth and proper map, then there is a push forward operator that maps currents of some dimension to currents of the same dimension. And again, it's defined to be the adjoint of the pullback of differential forms. Okay, so how about an example? So if M is an oriented, that's an important word here, oriented M-dimensional embedded submanifold in Rn of finite volume, then we can make it into a current. Okay, so the notation here is sort of funny double brackets. And so that's going to be an M-dimensional current defined in the following way. So when we are given, we need to say how it acts on differential forms of degree M. Well, it's going to be by integration over the manifold, right? And against this thing here, which is at each point, it's an M vector. It's a multi-vector of dimension M, and at each point it's a orientation of the tangent space, and we integrate with respect to the M-dimensional measure. Okay, so that gives a current. Now, I need to say a word about the mass because it appears in the isoperimetric inequality. So we can either understand it as a number or a measure. So the number is simply the usual volume of the manifold. And then the notation here, double bar, is for a measure. So it's a finite Borel measure in Rn. It's simply the M-dimensional measure restricted to that set, that manifold M. Okay, so okay, that's the mass in a special case. Now it turns out that mass can be defined for every M-dimensional current. And so mass of boundary 2, and the sum of these two is called the normal mass, and in general it can be infinity, but it is defined as a number between 0 and infinity. Now I need to give you at least some examples of normal currents. So here is how we can do. So let's look at this line here. So I want to look at finite sums or possibly infinite sums, right? So series where here I have MJs, they are like on the preceding slides. So these are currents associated to smooth manifolds. They're of class C1 and they are all in this box here, right? So I fix a box, right? And they're all in that box. And then GJ, GJ is an integer, okay? So it's just a constant multiple of this. Of course, as a current, it makes sense, right? And so we need to make sense of infinite sums. Well, for instance, we could talk about weak star topology under this extra condition here. I'm not going to get into the detail. The idea is that infinite sums are there as well. So they can have a pretty complex structure, these integral currents. So how about the push forward of such objects? Well, we can push forward integral currents by Lipschitz maps. Okay, so first of all, I don't need to require properness now of the map simply because they have compact support by definition. Remember, they support it in boxes. But the main point is Lipschitz is enough. We don't need smooth. However, it is worth and important pointing out for this talk that Hölder continuous will not do. Right? So for instance, if we work in the, I don't know, a semi-algebraic category and we have a continuous semi-algebraic map, well, what we know is that it's Hölder continuous. And so we cannot immediately use it to push forward an integral current. In fact, we cannot in general. So Lipschitz here is an important word to be able to push forward. And then once we push forward, the mass of the push forward is controlled by the Lipschitz constant of that map to the power dimension of the current times the mass of the original current. So that's one important construction. Another one is the following. So if we have a current, an integral current, so think of an infinite sum of manifolds or something like that, and A is a Borel set, then we can restrict the current to that set. So instead of integrating over the whole manifold, we just integrate over the manifold intersected that set. So this is defined as a current. However, it may not be an integral current because of boundary problem. So the boundary of this need not be an integral current itself. However, if U is a Lipschitz function, then we can restrict T to a sublevel set of U and still have it be an integral current, not for every R, but almost every R. And the last thing that we want to know about currents is we can slice them. Well, that's pretty cool. If we are given a current T of dimension M, now M must be greater than or equal to 1. What we want to do really is we want to build a new current, one dimension less, which should be the sort of the intersection of T with a level set of U. Okay, so we have three data here, T, U, and R. So the notation for the slice will use these three pieces, right? And so, of course, that doesn't completely determine the current because we need to match the orientations or something like that. So here is the picture down there. Let's say that T is two-dimensional. It's the surface of a torus, and we have cut a slit in it here. So there's a little opening, and so U is a projection on this line R, the horizontal line, and R is here, and so the level set is a vertical plane, right? Oops. Yeah, whatever. So the level set is a vertical plane. Oh, I can move it. So I'm gonna slice the torus here and there, right? And so what am I gonna get? Well, I'm gonna get a circle, and here I'm gonna get a piece of a circle because there's a hole there. So if you stare at this picture for 5 minutes, you will find out that this formula actually defines the slice. And then applying the boundary to this formula, you will find out that boundary and slice commute up to a sign. Okay, so now we have our vocabulary for currents. Is there any question regarding this? So the first thing to do is to prove the theorem locally. So this will be based on the following result by Guillaume Valette. From now on, A is always going to be a compact subanalytic set. Every point of that set admits a compact subanalytic neighborhood K and a Lipschitz deformation retraction that maps K to the point A. Now, of course, that there be a subanalytic one, a continuous subanalytic one is one thing, but the main keyword in Guillaume Valette's result here is Lipschitz. And that will be, of course, critical for what we're going to use it for, which is filling holes. So mapping currents. This is how we're going to use it. So let's look at this picture. So suppose we are given now a current J of dimension K in that neighborhood. And J is a cycle unless it is zero dimensional. Okay, so if J is zero dimensional, no extra condition. If not, it's a cycle. Well, and then we're gonna make this new current here. This is filling the hole. We're gonna look at J times the interval 0, 1, and then map it with this contraction. So that gives a new current, one dimension more. We call it capital H. Now, what is the boundary of capital H? Well, the boundary of capital H is J, if K is strictly strictly positive, because J is a cycle. The picture is here on the left side of the slide. Sorry, yes, that's right. The left side of the slide. So the cycle J is this wiggly curve here, and then H is the filling in red. Of course, in general, this need not be full dimension, right? Depends on, I can just, draw in R3 or whatever. So, and in case K equals 0, then the current J is, 0 dimensional. So for instance, just a Dirac mass. And then H will simply draw a curve from that point to the point A. Now, in that case, the boundary of H, so that curve, is not going to be just J. There's an extra contribution at the point A, right? So there's a certain multiple of A that depends on the total multiplicity of J, okay? So in both cases, however, the mass of H, so that's sort of the length or the length with multiplicity of this curve here, or the area with multiplicity of this disk here, is controlled by the mass of J, which is the length of this curve in the left case, or just the total multiplicity, absolute value of total multiplicity in this case, right? And then there's a Lipschitz constant. Okay, so we will use this all the time. We will call it filling, maybe. And then the other property that we're going to use is based on a result of Adam Parusinski in 1994. And it says the following. So what we're going to do is this. We're going to want to look at links. So I'm going to look at two links, right? So this one and this one. So the links are at different radii, right? So I look at A intersected a sphere, centered at A, and then here radius lambda r, and here radius mu r. So of course, if say lambda mu less than 1 and r sufficiently small, then these are homomorphic, but we want more. We want that they're actually by Lipschitz homomorphic. So this is not going to be true in general. We need to keep these parameters lambda and mu away from 0, of course. So the result is that because we want them to be by Lipschitz homomorphic with a constant that doesn't depend, of course, on these lambda and mu. So for every A, if R is small enough, then I can find a range of lambda and mu's that's between 1/2 and 1, such that these two links are actually by Lipschitz homomorphic with a constant that depends only upon A, capital A, and R. Okay, then we can also do this with finite unions of links, but I'm not gonna get there. I'm not gonna get to use this, so let's skip this slide. So the proof we'll use, we're now trying to prove this linear isoperimetric inequality. So the proof will use a covering of the set A, but the covering will actually depend on the current S0 that we are given in the first place. How it depends on that will appear in the course of the proof. So first we start by covering A with finitely many open balls, BAI RI half. That's using the compactness of A. And these balls are chosen such that the BAI RI is included in this KI corresponding to the Guillaume-Valette result, so that there is a Lipschitz deformation retraction HI on this KI, and then RI is also small enough for the link theorem to hold. So now the adjustments will be made by changing the radii of this ball here, right? So we will choose balls in between the BAI RI half and BAI-RI. So we will we will choose radius in the form of a lambda I-RI that's kind of in between. Okay, so here's this notation vector lambda. So we will need to choose finitely many of them. And the choice will be made according to the measure of S0, the measure of boundary S0, the slices of S0 of boundary S0, etc. We will see how they appear in the course of the proof. Right, so let's just have an abbreviation now for this ball here. So, of course, these balls, these open balls, they may overlap, right? So we will try to disjoint them to start with. So let's call W1 the first ball. So it's U1, right? So W1 is U1, whatever. And W2 is U2 minus the closure of U1, and then we keep doing this inductively. So now, of course, A is included in the union of, in the union of the WI's, the closure of these unions, and then the boundaries of these WI's, they are in the unions of n-1 dimensional spheres. So let's look at a picture. If I have three sets, U1, U2, U3, then the W1 is just a U1. The W2 is an open set, it's this one, and the W3 is an open set as well. In other words, the union of these W's does not cover A, okay? We are missing, sorry, no, yes, we are missing an interface here, right? So this part is missing. So we will need to be a little bit careful at some point. Okay, and of course, yeah, this part is missing as well. Okay, so first of all, we would like to use this near partition to write the S0 as a sum of its parts in each of these WI's. We would like to write this. So that sort of S0, you know, restricted to means, you know, intersection, this open set or whatever you want to think about it. And same thing for boundary S0. Now, of course, this is not true because simply the WI are not a partition of A, the ambient space. There might be some pieces missing that are in these interfaces here. However, the first point we can make is that if there, of course, there might be an intersection, but can there be an intersection with big measure, right? So remember, the S0 has some measure, and for instance, if it's a line and a circle, well, that's fine because the intersection is just a point which is length 0. But maybe sometimes you see the current could sort of use, right, this and then do this. But it cannot do this many times, right? It cannot use many of these spheres with positive measure, only countably many. And so we can choose the lambda I, so the balls, so that in fact this sort of equality holds here, and that means that we have this equation and this equation. So that's the first little adjustment that we make to the UIs and hence the WIs according to the S0. So now, I guess I should put an I here, maybe, whatever. It's not a nice I. So we will try to apply these filling methods in each of the WIs. So we look at the boundary of S0 in WI, that's a 0-dimensional current. And we fill the hole, right, with this contraction, right? That's fine, that makes a 1-dimensional current, kind of a bunch of curves maybe, and we call it EI. And we would like to use this, right? Sum these EIs to have our current that we are looking for, the S. Well, sure, the mass of EI is controlled by the Lipschitz constant of the contraction times the mass of boundary S0 in that open set here. right? It's this thing, the mass of that. So that's all fine. When we will sum these up, we'll have the mass of boundaries, boundary S naught. However, if I sum if I do a sum here, oh yeah, that's great. If I do a sum here, I won't have just the boundary S naught. I will have extra terms, right? So these GI here are the total multiplicity of the S naught in these open sets WI. So I need to make a little correction for these. So now I will assume, which is no loss of generality, that A is connected, and I can choose curves gamma I with endpoints AI and A1, so going from AI to A1, and whose length is less than a constant depending only on A. And then our current S is simply the sum of all these curves plus these. So what I have added now, so these things here, I can compute the contribution to the boundary, which is this. Well, the boundary of a curve by the fundamental theorem of calculus, there's just 2 Dirac masses, right? And then the second one here will remain there. And I claim that the first contribution disappears. That's because the sum of the GI is simply 0, because that's the total multiplicity of this current, and this current is just boundary S naught, and because boundary S naught is a boundary, it has total multiplicity 0. So that proves the case K equals 0. Now, the case K larger than 1 is going to be proved by induction on the dimension of the ambient space, right? Let's try to do that. So our goal is to repeat, the first step will be to replace S naught by a new current S1, which is a modification of S naught in this first ball. And the modification is in order that this new current now has no boundary in the ball U1. Okay, so I push away, if S naught had some boundary in U1, I just push it away outside of U1, or I try to. But in doing so, I don't want to increase too much the mass of S1. It needs to be controlled by the mass of boundary S naught. So how to do that? Well, I will slice with the distance function to A1. So of course, the level sets of that are spheres, right? So I slice S naught. I consider some spheres, right, to slice S naught. Okay, now that's a current P1, but you see it lives in this set. The original set A intersected a sphere. And that set is 1 less dimension than the dimension of A as a compact subanalytic set. And therefore, we can apply by induction the linear isoperimetric inequality to this P1. Of course, now we assume K is larger than 1. Right? So we assume it, we apply it to this P1. Then we find the Q1, yeah? It has the same boundary as P1, and its mass is controlled by a constant times the mass of boundary P1. The constant is given by induction. Okay, so now I will use that to fill the hole, right? So I have my boundary of S naught that is in U1. I want to get rid of it. So I add this Q1 that I found now on the sphere, right? And I add these two up, and then I fill the hole using this. This is a cycle, we will see it. So I create this new H1, yeah? Well, the mass of H1 is controlled by, is less than the mass of the J1, right, times a constant, and the mass of J1 is controlled by the mass of S naught, that's fine. And then the mass of Q1, which is less than a constant times the mass of boundary P1, because we applied the isoperimetric inequality by induction in this sphere. Okay, fine. Then let's compute the boundary of Q1. The boundary of Q1 is the boundary of P1, because we solved again an isoperimetric inequality by induction. P1 was a slice, boundary and slice commute, and by definition of slice, we get this. Okay, good. So this equation here actually proves that J1 is a cycle. If J1 is a cycle, then by the filling theorem, the boundary of H1 is J1. Then I look at the definition of S1 that I have here. S1 is S0 minus H1. Well, I just put, you know, the boundary of S1 is boundary of S0 minus boundary H1, which is J1, and I put the definition of J1, and oops, this is a minus sign, and I get this. Now I look at it, well, you see that the boundary of S0, the part that was in U1 has disappeared. I removed it. And Q1 is supported in the sphere. It doesn't have, it's no supported in the open ball U1. So I did what I wanted. The boundary of S1 doesn't live in the open ball U1. The mass of H1 is bounded by, oops, here I have mass of boundary P1. This one needs to be controlled. So I'm getting close to using all my time here, so I will finish soon. So if I had my boundary S0, say, as a surface, right? This is a surface. And suppose this surface has all these little bumps here, a million little bumps. And suppose I had just sliced at this radius, and so that the slice of this surface by the sphere is this curve, which is very long curve. And when I will use it to fill the hole, there will be this contribution, this surface whose area is much larger than the area of boundary S0. That's bad, that's bad. So what I need to do is I need to choose a different radius for slicing. How can I do this? Well, I can observe that the integral of the masses of these slices is actually bounded by the Lipschitz constant of U1, which is this number, times the mass of the boundary S0. But that's a formula. And then I apply Chebyshev inequality to find the good lambda, such that this is not much bigger than this. So of course, there's always new constants contributing. So the next step consists in trying to keep doing this. Right now, push the boundary of S1 away from the other ball. So we always want to do that. Find a H1 to HL whose mass is controlled by a constant times the mass of the boundary of S0. Then SI is SI minus 1 minus HI. And the boundary of SI is supported away from the first I balls. So in particular, when I equals L, there will be no more boundary. So boundary is empty, support means is 0. Then of course, S can be taken to be the sum of these HIs because its boundary will be a boundary of a finite telescopic sum. Only first and last term remain, but the last term is a cycle. And the mass of S will be this. So I will just indicate a problem that occurs as soon as you try to do the second step, is that unfortunately there's going to be part of the S1 that lives in here and will not be in there, and this will cause some problems, but I guess I stopped because I used up all my time. So finishing this induction will actually prove the theorem.
Okay, let's thank the speaker. Any questions? Hussein?
Thank you very much, Thierry. So, what's one of the directions which are interesting for someone working in singularity theory is to know if we can find invariants, because in your isoperimetric inequality, you have this mass with less than a constant times a mass to some power. For instance, if we consider the singularity that, which let's not think about the singularity, but we have the example, the algebraic example with z to the n equal x to the 2 plus y to the 2, z to the power 2m. So can we find, is the constant determined somewhere by this m? And the issue is, if we imagine that we have a singularity which is somehow constructed with many of these horns, is this constant determined by a kind of minimum, or is more subtle, or do we know how more subtle it is and how it works?
Yeah. So thank you for the very interesting question. I can detail the answer, but the bottom line is I don't know. So of course, on this particular example that we looked at, the Q could depend, of course, of the order of the cusp. Yeah. So of course that's true. You can do the explicit calculation there. That's a true fact. Now the proof that we have will never give anything better than a power 1 in the other in the isoperimetric inequality. So I don't know whether there is a general theorem. I mean, apart from the examples that, for which you can compute explicitly, I don't know that. So there's two things, right? The power is the one thing, and then there's also a constant in the isoperimetric inequality. So of course, if you follow the proof, the constant will depend on the, on the Lipschitz constants of the contractions, how many sets there are, and many other things. So it's extremely unoptimal, right? It's not no optimization, pessimization, right, for the constant kind of. So there's also an interesting remark there that, for instance, as far as a Poincaré inequality goes, for instance, one could prove it using compactness. So for those who do a little bit of function analysis, one way of proving these things is to have a compactness on the class of functions, say. And it turns out that in these even algebraic sets, one cannot do that. In the simple case of a cusp, even for codimension 1 on the surface, I can show that there is no compactness method that will ever work for kind of, not mysterious, but really annoying reasons. So the constant is bad, but it's not because the proof is by compactness. The proof is kind of nearly as explicit as it can get with the idea. But of course, so for the power, it's just because we do a contraction, and I mean, when you do that, it's like the area of a cone, right? When you compute so you have a circle and you do a cone with a contraction, the area of the cone is actually a multiple of the length of the circle, and you can't gain anything there, right? So because that's the construction we use, there's no hope for getting a power. And yeah, so I don't think it's useful to classifying singularities.
Okay.
Yeah.
Thanks.
Can I ask a question on what you just said, Thierry?
Yeah.
So if you had something a little better than a contraction I guess the contraction comes from Vallet, right? The Vallet paper.
Yeah.
If you have something like the contraction also, I mean, it doesn't only preserve distances, but it also contracts them in some directions. I mean, you would have to be precise in what this means.
Yeah, you have to.
Okay, I want to avoid it now. But so okay, if you can prove that the contraction is strict, so strictly better than 1 Lipschitz. I don't know if that's possible. If you can say or give a Vallet theorem for let's say a semi-algebraic set,
yeah,
which is defined with up to power q polynomials, can you get some better contractions?
Well, it's very hard to guess, right? I mean, maybe in the top dimension because you use all the area, but as soon as you have something wiggling of a high codimension in your ambient algebraic set, it's most likely that whatever information you have is not going to be enough. But I don't know. It depends on what it is. So I don't know. I'd be suspicious. But yeah, it's possible.
Thank you.
Yeah, you're welcome.
Okay, if there are no other questions, let's thank Thierry again.
Thank you very much for the invitation. It's very pleasant for me to talk here. Thank you.
Thank you.
Okay, so I suggest we take a 5-minute break. Our next speaker is Nicolas Dutertre from Angers, and he will talk about principal kinematic formulas for germs of close definable sets.
Okay, thank you very much. So I would like to thank the organizer for organizing this meeting and inviting me to give a talk. The goal of my talk is to give a principal kinematic formula for germs. So it's a new kind of formula, but before I will recall what a kinematic formula is. First, I will give a very short introduction, historical comments. Then I will define the Lipschitz killing measure. Then I will recall some known formulas, integral geometric formulas known for definable germ, subanalytic germ. Then I will state the principal kinematic formula that I found. And then if I have time, I will prove it in the case of conic sets. So let's start with the introduction. So the search for kinematic formula is one of the main goals of integral geometry. And such formulas have been proved in various contexts by various authors. So, for example, it was proved for convex body by Blaschke and Hatzbiger. For manifold, it was proved by Chern, and for manifold with boundary by Santalo. There is a version for PL sets due to Schigger, Müller, and Schrader. For set with positive reach, it is due to Federer, the same Federer as in the previous talks. And then I will focus on this situation. So for subanalytic set, it is due to Fu, and more generally for sets definable in an O-minimal structure, it is due to Berning, Poker, and Cooper. So first I will define Lipschitz killing measure. So I start with a compact definable set equipped with a definable witness stratification. So the fact that it is possible, it is due to Lua. Then I consider f a C2 function, definable function defined on R to the n. So what is a critical point in this situation? So the point P in X is a critical point of f restricted to X if it is a critical point of f restricted to the stratum SP that contains P. Okay. So we have the notion of critical points. And then we can associate to each isolated critical point, I can associate an index, which is 1 minus the Euler characteristic. This is the negative minor filer of f at P. So you take the level f equal fp minus delta, and you intersect with a small ball. So this is a negative minor filer. And here always delta is smaller than epsilon, which is smaller than 1. So I can make a picture. So I make a picture, I will make a drawing on the board. I hope you can see. So let's take X to be a very simple picture. This is a parallelogram, two parallelograms. You can click on this case. Click on the picture. It will be big. Yeah. Yeah, if you click on the picture, it will become big, right?
Maybe you use the red one, the red marker. I think one of those is better. Let's see.
So this is my set X. So it is stratified by this strata, which has dimension 2, 4 strata of dimension 1, and 4 strata of dimension 0. Okay. so in that case, I will consider F as a projection on this oriented line.
You said how many stack of dimension 2?
One. Sorry. So I have 4 critical points. This one, this one, this one, this one. And if I can compute the indices. So here you take a ball, you take a small negative level here. So you see it doesn't touch X. So the minor fiber is empty. So the index is 1. And here, project here, and then the negative fiber is something like that. And you see that it intersects X. And the other characteristic of this intersection is 1, so the index is 0. And here, similarly, the index is 0. And index is 0. So this is just a illustration. So now, with this index, I can define the Gauss-Bonnet measure. So first, we note that there exists a definable set gamma 1 in the unit sphere, which has dimension strictly less than n-1, such that for V not in this gamma 1, the function V star, which is just a product scalar product. Oh, sorry, this should be V here. This is a scalar product with V. So this function has a finite number of critical points. Okay. So with this lemma, I can define the Gauss-Bonnet measure. So I take U, the Borel subset of X, and I set the lambda 0, the measure lambda 0, evaluated on U, it's just this integral. I take the integral of all the unit vector, and I take the sum of the indices of all the critical points. Okay. And I put the index to be 0 when X is not a critical. So this defines a measure. So I can give a very quick example, which shows that it has some geometric meaning. So if X is something this, here, and here I have alpha, the angle is alpha, and I will evaluate the Gauss-Bonnet measure on a small ball near the edges. And then, what is the Gauss-Bonnet measure? So we have, so this is X. Here it's B, it's a ball, small ball around the, and then the Gauss-Bonnet measure is pi minus alpha divided by 2 pi. So this is exactly the angle, the variation of the normal vector here. It's a kind of it measures the variation of the normal vector. So it has a geometric interpretation. So this is the Gauss-Bonnet measure. This is then to define the Lipschitz scaling measure. So I take U Borel subset, and for K between 0 and n-1, I put lambda n minus K evaluated at U. I cut X with a affine space of dimension K, and I made the average, the mean value. Okay. So you make section with affine planes, and then you compute the Lipschitz scaling measure of the restriction, the Gauss-Bonnet measure of the restriction, and then you make the integral. So this is the affine Grassmannian of affine space of dimension K, and Cnk is just a universal constant. Okay. That depends on n, only on n and K. So now I can state the. So I just give some remark. So if D, yes, D is the dimension of X, then all the Lipschitz scaling measures they vanish for D greater, for the index for K greater than than D. And if and the lambda D, the top Lipschitz scaling measure is just the Hausdorff measure, just the volume. So D is volume. So in case Fx smooth is smooth, then you can recover. You can express the lambda k in terms of the usual Lipschitz scaling curvature, just the integral over U of this Lipschitz scaling curvature. I don't define the Lipschitz scaling curvature, but you can define it with a second fundamental form. So we recover something usual, something well known in the case of a smooth, the smooth case. And the last remark is that we have this Gauss-Bonnet measure, Gauss-Bonnet theorem. So if we evaluate lambda 0 at x, then we recover the Euler characteristic. Okay. So this is a generalized Gauss-Bonnet formula. So now, so this is the main topic.
Here x in 3, x is what is x? X is any definable sum.
X is a smooth definable set.
In 2 and 3? 3 is smooth also.
Wait, what? No, 3 is general.
It's general, yeah. What if general means
definable.
Definable and non-minimal structure.
Compact definable.
Okay.
Yes. So next. So what is a kinematic formula? So the Lipschitz scaling measure satisfies the following kinematic formula. So in this setting, this is due, as I mentioned in the introduction, this is due to Fu, Bernig, Rocker, and Cooper. So you take two compact definable sets X and Y, and you take U and V two Borel subsets. Okay, and then what is following the kinematic formula? So you integrate. This is a set of affine direct affine isometry, and you move Y, you intersect with X, and you make the mean value over this of all the intersection. You compute lambda k, you make the mean value, and then you can express it as a polynomial as a you can express them in terms of the Lipschitz scaling measure of X and Lipschitz scaling measure of Q. You have this approach. And this PQN are defined. This is the volume of the sphere, of the unit sphere of the dimension. This. So this is the general kinematic formula. So let me give a particular case. When k is 0, then it's called the principal kinematic formula. And I gave a simpler expression, simpler formula. So you take X and Y compact definable set in Rn, and you make the mean value of those Euler characteristics. So you have X. Maybe I can make a picture. So you have X, something like that. Y, something like that. So you move Y with a direct isometry. So it gives you intersection. You compute the Euler characteristic, and then you make the mean value. Right, but then you can move also Y like that. So this integral, this mean value of Euler characteristic is expressed in terms of the total, let's say, evaluated Lipschitz scaling measure evaluated on X and Y. Okay. So it's important in integral geometry because it contains many other integral geometry formula. For example, if Y is a ball, then you recover the volume of the tube. And if if y is
if y is a ball, you said you recover what?
the volume, the formula of the volume of the tube, general version of the tube's formula.
Okay.
Okay. You can take also y intersect a ball intersected with a plane, affine plane, then you recover the linear kinematic. So this is a formula in the global case, let's say. Now I will present some results for local germs, for local versions. So yes, that's what I write here. Find a similar formula for germs of closed definable sets. So let me start with some unknown formula. So the polar invariants, they were defined by Comte and Merle. And there are real versions of the local vanishing Euler characteristic that were, I think they were defined by Kashiwara. They were used by Brzezinski, Dobson, Kashiwara, and also by Leon Teissier. So what is the polar invariant? What are the polar invariants? So you take X. So this is not the original definition, but it is an equivalent characterization. So you take X, a germ of closed definable set. You take A between 0 and n. And what do? You take H of dimension n minus k. So this is a linear space. You move it a little in a direction v. You take a vector, unit vector. You move it h in the direction of v. Make a small truncation, very small, and you intersect with the ball. So this gives a kind of inner fiber, and you make the integral over the sphere and over the Grassmannian. So, make a picture. Rough picture. So, X is something like that. H is this. And I choose V. And I move H slow a little in the direction of something like that. And then you intersect with a ball, and you get a kind of generalized kind of real minor fiber. So these invariants, they were defined by Comte and Merle as a real version of the local vanishing Euler characteristic. Yes, so let me give some remarks. So if D is a dimension of X and D0 is a dimension of the stratum that contains 0, then we have this information. Sigma 0 until sigma D0 is always 1, and sigma D plus 1, sigma n, after D, they all cancel. They all vanish. Okay, so what did they do? Comte and Merle, they give some kind of integral geometric formula for this polar invariant, and they give formula that relates the polar invariant to the Lipschitz scaling curvature. So this is a big formula. So let me give. So they call this invariant Lipschitz scaling invariant. So you intersect X with a ball, you evaluate lambda k on X intersected with a ball, and you divide it by these terms. This is something finite, and you can relate those local curvature to the polar invariant through this formula. And, you have those coefficients defined in terms of the volume of balls. Okay. So this is the first thing they do. Particular case, interesting particular case is the last non-trivial. When D is a dimension of X, then the last non-trivial equality is lambda D log is equal to sigma D. But in this case, lambda D log is the limit of the volume of this volume divided by dD epsilon D, and this is the density. Okay, so the last formula, this equality, it was proved before by Comte, and it is a Cauchy constant for the formula for the density. Okay. what does it say? What does it say? This formula. We just take x. Here it's two-dimensional. You intersect it with lines close to the origin. So it gives you a number of intersection points, and the mean value, the integral of all these intersection points, is the density. This is the meaning of the formula.
Can you repeat this? So you take x and then what? You can.
Here you have the surface.
Yeah.
You take a line passing through the origin, you move them a little, and you count the number of intersection points.
Okay.
And you make the mean value.
Okay.
And you recover the density. Okay. So then they prove the following real version of a result of Léon Teissier in the complex case. And this was improved later by Nguyen and Valette. So you take x, okay, here this is a cut and paste mistake. You can put a definable.
Okay.
So you take x, a closed definable set, dimension b, and you suppose that it is equipped with a Verdier stratification. You take y a stratum, and then the following function. So y, you associate the polar invariant at y, and also you can associate the Lipschitz invariant at y. And these functions are continuous. So this is a so in complex case, Bernard and Tian, they proved that they were constant. So okay. So now I in a paper I introduced the following limit. Okay. They are a bit different. I call them gamma limit, lambda limit. Sorry. So you take the measure lambda k in x, you evaluate it on the board, and you divide by the same terms here, bk epsilon to the k, and you get new numbers. Okay.
Yeah, sorry. My fault.
Yeah. Sorry.
So now go down.
So you get new numbers that I call lambda k lim. Okay, is the name. So first, we remark that they are not equal to the lambda k log are different from lambda k lim. Okay, you just take the first easiest example, x is R2, then lambda 0 log is 1, lambda 1 log is pi O2, but the other they vanish. This is due to here the fact that the strata of the link, they don't appear here, they don't have contribution. Okay. So I prove this result. So here you can replace subanalytic by definable. I prove the following formula that relates the lambda lim to the sigma, to the polar invariant. Okay, so lambda k lim is sigma k minus sigma k plus 1, and lambda lim is sigma n. Because it's a bit simpler than a container formula. Okay. So now what? So question. So this is related to the first question that the goal of my talk. So what happened? What happens if I replace my n minus k plane H by any closed any germ of closed definable set? Okay. So this is what I prove. I did that last year during the lockdown period. I had nothing else to do. So I take x and y, two germs of closed dividable set. Then I can express. I get the following kinematic formula. So I integrate here. I don't integrate over the set of affine direct isometry. I integrate over SON, this is a set of linear direct isometry, times Sn minus 1. So I take x, I move y a little, or not a little, and then I translate it in the direction of v. And then I take the intersection with a ball. So this is the Miller fiber, kind of Miller fiber. Yeah, I take the limit, and then I make the integration over this manifold. Okay. And I can express, I can relate this integral to the invariant I've defined just before. Here, take the lambda I lim, and here's the polar invariant. Okay. So this is the result I wanted to state. So here, you see, you relate the mean value of Euler characteristic to some kind of curvature, the curvature of x and y. So let us look at a very special case. So let us specify this kinematic formula when the two sets have a complementary dimension. I mean, D is the dimension of x, E is the dimension of y, and D plus E is N. So I denote by x to the D the union of the top dimensional strata of x, the regular part, say, and y to the E is the regular part of y. And then we get the following corollary, which is a generalization of the Cauchy-Croston formula of Comte. So what does it say? So the following formula holds. So here, instead of the Euler characteristic, because generically the intersection is a finite set of points. So what do I count? I count the number of intersection point of xd with this set gamma y e plus a small translation. And here we find the product of the densities. Okay. If you take H to be E dimensional space, linear space, then here you will have one, and we will recover George formula. Okay. So how much time do I have?
I think 5 or 6 minutes.
Yeah. Say okay. So I will in the rest of the
maybe 7.
Yeah. 7. Okay. I will try to give some ideas, but it's quite technical. Mm-hmm. So I will give idea of the proof in the case of conic sets. Okay, the simplest case. So first, I need a spherical kinematic formula. So here I will work in the sphere. So X is a compact definable set in the unit sphere, and Y is any definable set. So I have the following kinematic formula. Here I compute the mean value of this key Euler characteristic with a compact support of this intersection, and I relate to this lambda tilde I. There are the spherical Lipschitz measure. As in the case of a Euclidean space, you can define also Lipschitz measure for space in sphere. I don't give the definition, but it's possible. And here we have this intersection of X, this intersection of Y with a linear space. So this is the first step. So how do I prove this formula? So if Y is compact, it is just an application of the generalized spherical Gauss-Bonnet formula and the generalized spherical kinematic formula. So which are due to Fu and Berning-Brocker. So this is computation, not necessarily easy, but we apply a computation. And to get the result for any Y, we use the fact that any definable set admits a cell decomposition, and then we use additivity of TC, which is just this fact. Then I proved a new kinematic formula in the unit ball. So I take X a closed conic is important, definable set, and Y another definable set in the unit ball. Then the following formula holds. So here, yes, I mean the integral over SOM of solar characteristic of X intersected with gamma Y, and then I relate them to the Lipschitz curvature of X. These limits of Lipschitz measure divided by pi, and then I have this term, this mean value of the Euler characteristic. Okay, so how do I prove this formula? So the idea, maybe I can make a quickly picture. Imagine this is the ball here, the origin. First case, Y is not in the, let's say this is Y, and I use a radial projection. I use radial projection to apply the previous formula. Okay. In order to apply the previous formula. So that's what I say here. I assume first that the origin is not in Y, and I consider this radial projection. Then what do I do? So I apply Art's theorem to this radial projection. I use a previous spherical kinematic formula, and then this equality. I can relate the Lipschitz measure of X to the spherical Lipschitz of X intersected with the sphere. So yeah, you can see that with this idea, I can prove the kinematic formula in the ball, the unit ball. So this is the case. This is for the case when 0 is not in Y. If 0 is in Y, so I denote Y star Y minus 0. I apply the previous case to Y star. Okay, and I use this following this equality. So the Euler characteristic is just of X intersected with the gamma Y is just the Euler characteristic of X intersected with the gamma Y star plus 1, because I've removed one point. And then I use this kind of local Gauss-Bonnet formula. So this gives a formula for the this gives a proof of the formula of the kinematic formula in the ball. And then I can prove the kinematic formula for conic sets. So I take XY2 closed conic definable set. And then this is the formula in this case. In case of conic set, I don't have to take a ball. I can cut by the unit ball. Okay. I don't have to change the radius of the ball. So this is a formula in the case of conic set. How do I prove this? So it's a sketch of proof. I fix delta. I make the following change of variable. U equals gamma V for gamma in SOM. And then I have this equality, the integral over Sn minus 1 of the Euler characteristic of X intersected with gamma Y plus delta U intersected with the ball. Here is equal to this. Here, I mean, I can pull out gamma from this parenthesis by this change of formula. And then this, for this, I apply the previous case. So we apply the previous case to X intersected with B and Y plus delta V. And we get this. Okay. So this here. And here. And then after I make the mean value over SON, we obtain this. And then I just have to relate this quantity to the polar invariant. So I pass at the limit. Yes, before I need to pass at the limit, and I use a Lebesgue theorem, and I obtain this. So this is the left-hand side. This is what we want here for X, and for Y, we want the polar invariant. But this is very easy because if you fix Y, H and move a little Y, it's like fixing Y and moving a little delta. Then you need the new value. So we conclude with the following observation. So if I move a little Y in the direction V, and I intersect with H and take the Euler characteristic, it's like fixing Y and moving a little H. And then you make the V value, and you recover here, you recover the polar invariant of front. I think it's finished. I just wanted to state this formula, which is more complicated, but it is a formula that I conjectured before. The first formula I conjectured.
Yeah, this.
So here is the same. You take two germs of closed definable set, and instead of taking the here Euler characteristic, I just take the Gauss-Bonnet measure evaluated in the interior of in the interior of the set. Mm-hmm. So it's not the Euler characteristic. Mm-hmm. And then you have this formula. You recover. You relate to this sum of gamma I
from the I.
And then thanks for your attention.
Thank you. Thank you very much. Any questions, Bernard?
It seems an application of this would be a real Euclid formula. Suppose you take a real projective algebraic variety, stratified, and you want to compute the volume of the dual in the dual projective space as a function of the local densities of the strata along the strata of the boundary and the local polar invariance. I suppose one could write the formula using what you just explained. That could be an illustration of this, which it might be interesting to try to compute it for real.
Okay. you have a exertion of what you
I
said?
have a complex version.
So there should be exist a real one.
You can find it in the paper in the Annales of Toulouse, which I wrote. There are actually lecture notes with Arturo Gilles Flores.
Okay.
It's I don't know, between.
Yeah. I know.
And at the end, I explained precisely that the formula which relates the polar multiplicities with the vanishing Euler characteristic,
yes,
in the local case for the complex space, if you apply it at the vertex of the cone, it gives you a Euler formula. In general.
Okay. I see. Thanks for the suggestion.
I think there is also a version of this Euler formula with multiplicities, like Lyman generalizing for at least for hypothesis.
Yeah, but that was in the case of isolated. What I'm saying is this is completely general. You take any complex corrective variety with its canonical weakness stratification and using only the local vanishing Euler characteristics of the singularities and their general plane sections and the Euler characteristics of the strata and the general plane sections, you get the formula for the duo. Why I'm interested in this in the complex case, because it's a formula where you don't have to take cohomology or characteristic classes or anything. The only thing that moves in that is the hyperplane or the planes. You don't have to do any homology or anything like that, compute characteristic classes or anything like that. It's purely geometry.
Okay, thanks. We asked my student to do that.
Okay.
It's a good problem for a student.
Any other questions?
Yes, I have a question, if I may. So if we replace, instead of looking at germs, we look at sets, definable sets, and then we want to approximate a definable set by, say, a PL set, or a sequence of PL sets. do we understand how they need to converge for these numbers to converge as well? So some integral geometric defined number?
You mean, can we relate the Lipschitz scaling measure of the set to the Lipschitz scaling measure of the approximating function? I think it's done in the paper of Brocker and Cooper. They approximate the set by manifold with boundaries.
Okay.
And then they express the Lipschitz scaling measure of the set. They relate them to the as a limit of the Lipschitz scaling measure of the approximating sets.
Okay.
You need F conditions.
Please. Okay. If there are no more questions, let's thank Nicolas again. Okay, it's my pleasure to introduce Professor Maria Ruas from Sao Carlos, who will talk today about density of Lipschitz stable mappings.
So, hello to everyone. It's a pleasure to be here and give this talk. And I want to thank Tony for the invitation and extending my thanks to all the organizers, Pooneh, Hussein, and Bernard. And for the talk, I will take my video so that we have less problems with the internet. So I will report on results of the following works. So it's a paper, 2019 paper with Sourab Trivedi about Bilipschitz geometry of contact orbits in the boundary of the nice dimensions. Our work in progress was with Nhan Nguyen and Sourab Trivedi about density of Lipschitz stable mappings in the boundary of the nice dimensions. And a survey paper to appear in the handbook edited by Cisneros, Ledontran, and Pepsiadi, all the new results on density of stable mappings. So the subject of the talk goes back to the early years of singularity theory. I talk about stable mappings. So stable is smooth mappings from N to P, where N and P are smooth manifolds of dimensions N and P. And introducing the notation, C infinite of N and P denote the space of all such smooth mappings. And we give to the set the witness infinite topology. So to define a stable map, we need an equivalence relation. And in our case, is A equivalence. So A equivalence is change of coordinates and source and target. So we say that F and G are A equivalent if we can find diffeomorphisms H in the source, K in the target, commute in this diagram. So and then right away I can define stable map. A map is stable if there exists a neighborhood of U, a neighborhood U of F in the whole space, such that for every G in U, F and G are A equivalent. Of course, you can interrupt me to ask questions if you want. So we can get similar notions replacing in the previous definitions, say infinite diffeomorphism by homeomorphism, C0, or CL diffeomorphism for all L between 1 and infinite. So with these substitutions, we get, of course, the definitions of C0A equivalence and topological stability, right? So just going back here. If I replace H and K by homeomorphisms, we have the definition of topological equivalence. and the corresponding definition of topological stability. And similarly, when I replace by CL diffeomorphisms, we obtain CL equivalence and CL stability. So then I can summarize the problem, say the driving problems of singularity theory at those early years in the following way. So if I denote by SL, the subset of CL maps in the space of proper maps from N to P, proper smooth maps from N to P. So the question is to find the pairs of dimensions NP for which this set is dense, and if possible, to characterize the stable singularities. The aim of my talk is from one side to review these classical results and to bring to this context the notion of Lipschitz stability. It's by Lipschitz stability, but for short, I will say Lipschitz stability of smooth mappings. And posing the problem of whether the set of Lipschitz stable mappings is a dense set or not. So to my knowledge, this question has not been considered yet. So going back to the history, and we have to go back to the words of Haslett-Whitney, works of Haslett-Whitney, Henneton, and John Matter. Well, first was Haslett-Whitney, that many of us consider the founder of singularity theory of differentiable mappings. In the decades of 40s and 50s, in the decades of 40 and 50 of last century, Whitney wanted to understand the stable singularities and whether the stable maps form a dense set or not. In fact, he defined a stable map. He was able to prove in some cases, for instance, in this 1944 paper, he proved when P is equal to 2n minus 1. And in this magnificent paper that appeared in 1955, he characterized the stable singularities of surfaces to the plane and proved that the stable maps, when in this case, form a dense set. In fact, Whitney conjectured that the answer would be yes for any pair of dimensions. But René Thon, in his 1959 lectures at Bonn, he sketched the proof that stable maps are not dense when n equals p equals 9. And he formulated conjectures also on density of topological stable mappings that led to great development in singularity theory. I would like to present right away the Thon's example, showing that stable mappings are not dense when n equals p equals 9, right away, because it's the main example in the talk. So Thon gave an example of a genetic family of maps. So generic in the sense that it's a one-parameter family, generic in the sense that the union of the A orbits of these maps when lambda varies is an open set in the whole space. But however, when lambda is different from lambda prime, F lambda is not A equivalent to F lambda prime. So let me erase. Sorry. So this is the map, right? So we can see here that this map can be seen as an unfolding of the following. When I make u equals 0 for each lambda, I see that this map is an unfolding of the following map or family of map, better say, from F0 lambda is this quadratic mapping from R3 to R3. So for each lambda, I can see F lambda, big F lambda, as an unfolding of this quadratic map. And what Tom, in fact, did was to prove that this quadratic map from R3 to R3 defines, we can say, defines a net of quadratics, right? That is a unimodular family, right? So if lambda is different from lambda prime, these are not even linearly equivalent. And this is the main reason why this gives the counterexample for this map from R9 to R9. So, so this was back in 1959, as I said. And next came the work of Matter, John Matter, that from 68 to 71, he wrote a seminal series of papers in which he almost completely realized that the program proposed by René Thom. So the results that I want to quickly discuss in this talk are these two theorems, the two mother. Theorem A, where he proved that stable maps are dense in the space of proper maps, if and only if the pair NP is in the nice dimension. And however, he proved also that topologically stable mappings are dense in the set of proper maps for any pair of dimension. Mader also computed what are the nice dimensions. And so in this graphic, the horizontal axis is n, the vertical is p, and the nice dimensions is this open blue region here. So if you look at the line n equals to p, you see that the first pair outside the nice dimensions is exactly the pair 9 and 9 for the reason I just explained. So it was 20 years later, more or less, that under the Duplessis anterior wall proved that the set of C1 stable mappings is dense if and only if, again, N and P is in the nice dimensions. This is a very deep and difficult paper to read, and in which they study several invariants of C1 equivalence in order to get the result. Okay, so what we are trying to do. So to try to understand what are the pairs of dimensions in which Lipschitz stable mappings form a dense set, we defined in the paper with Sorab and Nia, a pair is in the Lipschitz nice dimensions if the set of Lipschitz stable mappings is dense. So our conjectures concerning this problem is conjecture 1, that the Lipschitz nice dimensions contains Mader's dimensions and its boundary. So this time we would have also the boundary as where the property of density of stable maps would verify. So conjecture 2 is just that conjecture 1 is sharp. In other words, if you take a pair in the complement of the union of the nice dimensions and its boundary, then the Lipschitz stable mappings do not form a dense set. In fact, the reason why we separate into conjectures is that we essentially have the proof of conjecture 1. However, we cannot say much about conjecture 2. In this paper, we can, to illustrate that we really hope that conjecture 1 is true, I sketched the arguments to see that density of Lipschitz stable mappings holds when n is compact and n equals p equals 9. I would like to emphasize that this in particular gives the first example of Lipschitz stable mapping, which is not trivial in the sense that the map is Lipschitz stable without being C-infinity stable. Our plan to prove conjecture 1, of course, has to draw over Mother's theorem A and B. So, and those theorems, they are based on the following steps. So Mother constructs a stratification in jet space. And so he proves that maps transverse to this stratification has the required properties. And finally, then we apply Thom's transversality theorem, or more generally, Mother multitransversality theorem, in order to obtain the result. So then we quickly go, let me see here. So we quickly go to the main ideas of the proofs of theorems A and B in order to pose our problem. So to study stability, Mother introduced the concept of infinitesimal stability as, in fact, introducing the infinitesimal tools to study stability, right? So going to the infinitesimal methods means you go from maps to vector fields and from diffeomorphisms to deformations, right? So in this diagram, we define then, let me call F star of TP the pullback bundle over any via F. And Tn and Tp, of course, are the tangent bundles of N and P, respectively. So we denote by theta F the set of sections of this pullback bundle. So more precisely is the set of maps from N to Tp, such that sigma composed with pi 2 is F. We call this space of vector fields along F. So in fact, these are all the deformations, possible deformations of the map F. Theta N indicates the set of sections of the tangent bundle, and as well, theta P indicates the sections of the tangent bundle TP. This definition has a local analog, which is easy to see, right? So we can define the concept of, sorry. Before that, let me give the definition, right? So the definition says that F from N to P is infinitesimally stable if for any vector field along F, you can find sections S of the Tn and section eta of Tp in such a way that sigma can be written as Tfs plus eta composed with F. So that means that you can write any deformation of F under this sum, which is essentially the set of all vector fields along F that can be written in this right-hand side of the formula. They form what we call tangent space of the equivalence. We can give the similar local definitions of this concept, but they are not really given, so I think I can skip the next slide and state this mother theorem that gives the following conditions which are equivalent to stability. So for a proper map, stability is equivalent to infinitesimal stability, to locally infinitesimal stability, and to the transverse stability that I will explain now. So the concept of transverse stability is the following. So if a mother consider the stratification, so now in fact, I consider JK and P for small n and small p as the set of jets with source and target 0, which is in fact the fiber of the K-jet bundle, JK and P here. So mother defined the stratification of JK and P by orbits of the group A in the jet space. And of course, this stratification of JK little n P induces a partition of the K-jet bundle. And we say that F is transverse stable if the K-jet extension JK of F is transversal to this stratification. This is, of course, a deep theorem that was developed in several of the papers Mother wrote in that period. And for instance, one has to apply the Mother preparation theorem, or Lagrange-Mother preparation theorem, in order to prove some steps. It's easy to prove that if F is stable, then it's transverse stable, right? As the set of transverse stable maps is dense. And but to prove that transverse stable implies locally infinitesimal stable, we need the preparation theorem. In fact, the expression to say that F is transverse stable is equivalent to say exactly a polynomial form of infinitesimal stable holds. Okay, so let me see how I am with the time.
Can I just ask?
Sorry?
Yeah,
Sure.
On this theorem, that is for smooth stability, CK maps, or when does it, what category is it in?
Okay, so here I'm considering smooth mappings, right? Smooth mappings and smooth stability. When I say stable, without specifying the differentiability class, I mean smoothly stable, okay? So I always consider smooth mappings, and in this theorem, I consider smooth stability.
Thank you.
Okay, so there's another ingredient which I should talk about, which is the contact equivalence. So Mother defined the contact group as an important tool to classify stable singularities. So the contact group is, I didn't define here because it's in general well known, but I just remind that I can say that it's the set of diffeomorphism. It acts on the graph of the maps. And it's the set of diffeomorphisms in the Cartesian product that leave invariant the source and brings the graph of one map to the graph of the other map. But from this point on, I would like to say that much of the construction, the necessary construction to prove Mother's theorems A and B, they are local. They are local. So, and then just to make the notation, I call epsilon n the local ring of infinite function germs at the origin, and Mn its maximal ideal. And I consider germs from Rn to Rp at the origin, that denoted by epsilon Np, where epsilon, and we can see that epsilon Np is a free epsilon n modulo of ring P. So let me also remark here that the local constructions leading to Mother's theorem, they hold also for real analytic germs and for complex, for holomorphic germs, right? But I'm only considering the theorem as stated in the smooth case. So the important invariant of K equivalence is the local algebra of the germ, defined as follows, right? It's just the algebra, this quotient algebra here, given here, where the denominator is the ideal generated by the coordinate functions of F. And it turns out that this is a complete invariant for the classification with respect to contact equivalence when we restrict to the class of finitely K-determinate germs. So if F, then, or here there's a mistake, here F is a germ in epsilon Np. It's finitely K-determinate if there exists a positive integer S such that the K orbit of F contains all the germs G with the same SZ as F, right? So these will be the relevant germs. In fact, Mother gave an important definition for the proof of theorems. He defined the maps of finite singularity type. Maps of finite singularity type as maps from N to P, finite singularity type, as maps from N to P with the property that all germs and multi-germs are K finitely determinate, and the restriction of F to its singular set, to the critical set, better saying, the set of non-submersive points. This restriction is proper and finite to 1. Finite to 1. Okay. So then, any question? So the two main results about K equivalence that I need is, first of all, is just what I said, that for k finitely determinate map germs, the local algebras are a complete invariant. In other words, F and G are k equivalent if and only if their local algebras are isomorphic as are algebras. So is there a problem with the sound, with my voice? It's some, can you tell me, please?
No, we hear you well.
So let me put, I have some kind of echo.
Oh.
So the main theorem Mother proved, which relates the classification of stable germs with K equivalence, says that if F and G are same-finity stable germs, then F and G are A equivalent if and only if they are K equivalent. So in fact, it happens that the A orbit of a stable singularity is a disk open in the K orbit, in its K orbit. So in fact, in the characterization of transversally stable, we can replace the A classification by the K classification. And of course, we can see that it's much easier to work with the contact equivalence as this complete invariant, which is the local algebra, is not so hard to compute, right? So I have maybe 30 minutes almost, right? Let's see. Okay, so let's talk a little bit about theorem A, Mother's theorem A, which says that stable mappings are dense if and only if the pair is in the nice dimensions. So the proof of theorem A is as follows. Mother construct a smallest Zarisk closed and K invariant set that we denote by pi K and P in the jet space, J, K, and P. It's the smallest one with the property that the complement, its complement in the space J, K, and P is the union of only finitely many K orbits. So then we call the set pi K of bad set because it is the set where moduli occurs, right? So the properties of the set are that the codimension, its codimension is decreasing as K increases. And we can find a K big enough for which the codimension attains a minimum. So, and we denote, when for this K, we denote the codimension of the bed set by sigma NP. So characterizing this bed set, so we can Mother computed the codimension. So he computed the codimension of the set in which moduli, the minimal set, the smallest set, for which moduli occurs. And so we don't need to go in details over the formulas, but you can see, for instance, when P is equal N here, we get that the codimension of the bed set is exactly 9. Okay. So we hope, in fact, the hope that we have in order to prove the theorem is that the bed set, of course, are the nice dimensions are the pairs for which the bed set has a bigger codimension, has a sufficiently big codimension. So in fact, the nice dimensions are the pairs for which sigma n and p is greater than n. So the meaning here is that if the codimension of the set is big, maps transverse to the stratification in jet space will not hit the set. So in fact, this is the idea, right? So if the pair is in the nice dimension, then we have a stratification of the complement of the bed set given by a finite number of contact orbits. And this stratification, of course, the set, as I said before, the set pi k and p is itself as a risk closed set. In fact, it's an algebraic set. And so we have a stratification for the whole jet space, but the relevant strata are given by orbits of simple, are given by simple k orbits. So this stratification extends to the whole fiber bundle. And so that we can apply Thom's transversality theorem to prove that maps transverse to the stratification in J, K, and P form a dense set. Well, the theorem B goes more or less along the same lines, but the proof is much harder. In fact, the sketch of the proof of theorem B was given by Matter in 1971 in the Proceedings of the Dynamical Systems, realized in Salvador, Bahia. But the complete proofs appeared in 1976 in two different works. But the book by Gibson, Duplessis, Loyenga, and Rhys Miller, and also a paper by Matter on the Proceedings of Plain-Sirbeck's conference, also in 1976. So both proofs are similar. And in fact, theorem B is a consequence of the following theorem, right? That if F from N to P is proper, and for some, and hence for all K greater than or equal to P plus 1, then K jet of F is multitransverse to Thom-Mader stratification. If JK of F is multitransverse to the Thom-Mader stratification, then F is topologically stable. So as I said, the construction of the stratification in this case is much harder, but what it is based in several properties. For instance, Matter proved the first stratification in which the relevant strata are mappings of are singularities of finite singularity type. And it follows from his results that mappings of finite singularity type, they have a stable unfolding. And the construction of Thom-Mader stratification takes into account the fact that we know how to stratify this stable unfolding of the maps from M to P. The Thom-Mader stratification is a Whitney regular stratification. And the maps transverse to the Thom-Mader stratification, they are Thom stratified maps. And the final step of the proof of the theorem consists in showing that the stable unfolding of F is topologically trivial along the moduli strata. And for this, it's necessary to apply the second tones isotopy lemma. So, and this is in fact the main point in which when we look from the viewpoint of the Lipschitz stable mappings, this is the point that we have to replace to obtain the result. So then let's go to the Lipschitz stable mappings. So first of all, we can immediately see that if for this discussion, I will assume that N is compact, just to avoid the discussion if Lipschitz equivalence, local Lipschitz equivalence can be replaced by Lipschitz equivalence, right? So let me assume N compact and F a Lipschitz stable map. Well, I think the main point to say here is that we know that for any pair of dimensions, N and P, the tone mother maps form a dense set. So we have already a stratification in jet space, and we know that maps transverse to these stratifications are topologically stable mappings. So if I have a Lipschitz stable mapping, then it follows that it's clearly equivalent to a tone mother map, right? Because the set of Lipschitz stable map is open, and then we can find sufficiently close to F a tone mother map, which is then equivalent to it. So the question is then, of course, to find conditions for a tone mother map to be Lipschitz stable, right? And I can also ask the converse. I mean, if I have a Lipschitz stable map, is it true that it's a tone mother map? So this last question does not hold for topologically stable maps. We have here this example of Robert May, he gave in 1973. So this is the graph of a map from R to R, right? That at the origin is equivalent to f of x equals x cubed. It's easy to see that this is a topological stable map. However, it's not a tone mother because this map is not transversal to any K equivalent stratification of the jet space. So do I have more, maybe 2 or 3 minutes? It's okay?
Yes, yes, okay. You do.
Okay, so the point of the results I'm trying to say to you is that at the boundary of the nice dimensions, we know much more about this tone mother stratification. So the bed set defined by matter in theorem A, so which is the set in which a modality occurs, cannot be avoided in this case, right? Because the boundary of the nice dimension is the set of pairs N in P for which the codimension of the bed sets is exactly N. So, and what follows is that then the relevant stratas of this tone mother stratification in this situation when we are at the boundary of the nice dimensions are the K orbits of dimension less than or equal to N, of course, right? But I also have a strata of dimension N which are unimodular strata, so made of a one-parameter family of contact orbits. So then we have to take from the bed set this unimodular strata, right? And in order to have my stratification in this case. So what happens is that, in fact, in the whole boundary of the nice dimension, except when n is equal 10 and p is equal 7, there is only one unimodular strata that consists in a relevant strata. This value 10.7 is exceptional. And in fact, we also have to consider a bimodular strata in the relevant part of the stratification. So of course, the bed set is the complement of this relevant strata in the previous bed set defined by matter. So then just repeating, I take the stratification with the orbits of codimension less than or equal to n, and I add to it the unimodular strata that I can identify, right? And this is the, for instance, in the case in which n equals p equals 9, right? The unimodular strata is exactly given by this local algebra of the tones example I introduced before. So just I don't have much time, so that goes quickly. What we did in the paper with Sorab, and we can also read about the other details about this in the survey paper, was a case-by-case construction of the tone-mother stratification in the boundary of the nice dimension. This part of the work is, in great part, is to collect from the literature the unimodular algebras, and one of main tests for this is the book by Wall and Duplessis. We proved in the paper that the tone-mother stratification is by Lipschitz K invariant. So the stratification of tone-mother has this property that it's by Lipschitz invariant with respect to contact equivalence, but we don't know, of course, whether, in which case it can be locally Lipschitz trivial, for instance. So in the case n equals p equals 9, I have here the list of all relevant strata. So the first ones up to C2K consists of algebras of stable singularities of codimension less than or equal to 9. And we have our family, unimodular family that I introduced before. So these are the relevant strata. Okay, so just to finish, to prove the density of Lipschitz stable maps is a property holding when n is compact and n equals p equals 9. There's only one thing we have to do. We need to prove that the family given by Ton's example is by Lipschitz A-trivial along the parameter space. So this is the work that we do in the paper with Nian and Sorab. And this is the most delicate piece of the work, because if one side, we know that the topological stability was obtained, by integration, by integration of vector fields, which are control the vector fields, continuous and control the vector fields in the case of tone-mother maps. The proof that we can modify vector fields in order to prove that they are Lipschitz is a very delicate work, which is based on a refinement of the construction given by Damon in his 82 paper about finite determinacy and topological triviality. I stop here because I'm sorry that for passing. Thank you.
Thank you, Cidinha. Any questions?
Yeah.
What does it say?
Terence raised his hand.
Terry?
Yeah,
Yeah, we hear you.
so I was wondering, we have the following situation where if we have the family terms that you put on your last slide, then we know from the work of Mistovsky that the family of discriminants is generically Lipschitz equisingular. And so the question becomes, do you have any insight as to whether you can lift these Lipschitz vector fields, which implement Mistovsky's program, over the maps F?
Okay. So Terry, what happens is that, let me go to the slide, sorry, here. When I look at this map, F lambda xu comma lambda, this is a stable map. This is a stable map from R10 to R10, okay? So, but
Yep.
what happens is that the discriminant of the stable map, the logarithmic stratification of this discriminant is not holonomic, which means that the strata lambda, the vectors tangent to the discriminant, they all are zero over the lambda stratum, right? So when you take a generic section passing through a given value of lambda, in fact, what you said is true, right? So a generic section, if you move the generic section with a lambda value fixed, right? You don't change the A class of your map F lambda, right? So the question is the Bilipschitz triviality along the parameter strata.
Right. So the problem is that, exactly as you said, you cannot get at these Mistovsky vector fields by trying to use vector fields, smooth vector fields that are tangent to the discriminant, because they're all going to be zero along the parameter axis.
Yeah.
That's a problem.
Yeah.
But nonetheless, they do exist. And so part of me wonders whether you can get your hands on them through Damon's work. And part of me just wonders about this question of what happens when you try to lift things back over the source. It'd be interesting, for example, because I'm thinking about in general, it will always be true. For example, if you have maps from where n is equal to p, that the discriminants generically will be Lipschitz equisingular. That's what Mistovsky proved. So there's going to be some phenomenon of the failure to lift these things over F if it turns out that the by Lipschitz stable maps are not dense. It'd be interesting to find out about that.
Yeah, sure. Just make a remark that I forgot to say, in fact, is that there's a miracle in our opinion in the boundary of the nice dimensions that makes the conjecture possible, is that all unimodular strata are homogeneous.
Yeah.
They are given by homogeneous algebras. Yeah. And if you go out of the nice dimensions and its boundary, so you have problems like in this slide, the last slides that I didn't show, in which you find unfoldings of Parusinski and his example, for instance, right?
Okay, any other questions?
Yeah, I have a question. So it's David.
Hi, David.
Hi. Very nice talk. You mentioned the example of May of a topologically stable map, which is not Tarmather, but it's not strongly topological stable in the sense that you cannot choose the homeomorphisms to vary continuously with G as you move G near F. And I know in the smooth case, Mather's proof of density gives smoothly stable maps where the diffeomorphisms vary continuously. Do your Bilipschitz homeomorphisms vary continuously when you get Bilipschitz stability?
Well, with the hypothesis that we are considering, we hope so, right? Because we are really working in the Tom-Mather stratification, right?
Yeah, I should mention that recently with Andrew Duplessis and Claudio Mirolo, I proved that strongly topological stable mappings are dense in all dimensions. So in a topological context, you can ensure that the homeomorphisms vary continuously.
Yeah, proper maps, right? Yeah.
Proper or quasi-proper in the Duplessis wall sense.
Yes.
Yeah, proper maps.
Yeah. Thank you.
Okay. If there are no other questions, let's take Sidinia again for the very nice talk. And with this, we finish the program for today. We resume tomorrow.
See you tomorrow. See you tomorrow.
See you.
Bye, everybody.
Hi.